Now we can start the program.
Good evening, all present this forum. On behalf of the Knowledge Institute of Technology, I am so happy to welcome all the participants, resource persons, our principal sir, and all the heads of the department and all our faculty members to this webinar series. So this webinar series will focus on how to do easy research. So in this aspects, we will organize 8 lecture series. The first series will start on today, followed by professor from IIT Bangalore and professor from Anna University, and our principal sir will take over the sessions. This first session will delivered by Professor Muthukumar sir from IIT Guwahati. On behalf of the Knowledge Institute of Technology, I am really happy to welcome Professor Muthukumar sir. I welcome Muthukumar sir, and I welcome all the participants throughout India. Most of the participants they are joined from Ahmedabad, Delhi, Haryana, and Hyderabad. So I am really happy to welcome all the participants from other states of Tamil Nadu, and I really so happy to welcome our principal sir, Dr. P.S. Srinivasan sir. He is a founder Knowledge Institute of Technology. I'm so happy to welcome all the participants once again. Now the session is handed over to Professor Sandhya Gundri madam for giving a formal welcome address. Session is over to Professor Sandhya Gundri madam.
Good evening to one and all participated in today's webinar series on effective research. Warm welcome to Professor Muthukumar from Department of Mechanical Engineering, IIT Guwahati. Welcome you, sir. First of all, we would like to thank you for accepting our invitation to present over your today's session with us, even with your busy schedule. Thank you, sir. Next, I would like to welcome our founder and principal of KOT, Dr. P.S. Srinivasan, sir, for today's webinar series. Welcome you, sir.
Happy in joining.
PSS sir is an instrumental in research. He has nurtured a seed at our research forum for that under that named process of everyone can do quality research. Welcome you, sir. Next, I would like to welcome our Director Dr. Stephen from Knowledge Business School. We would like to welcome our Vice Principal Dr. Visagavel, Placement Director Dr. Rajendran, and Training Director Dr. Thangavel for today's webinar series. We would like to welcome our faculty colleagues at KOT and friends. Last but not least, we would like to welcome the participants across nation. Today, you are going to enjoy the session with that Professor Muthukumar's speech. Takeaway from the home is under the topic, namely instrumentation and thermal engineering is today's top one. Thank you very much for that opportunity given. Once again, on behalf of Knowledge Institute of Technology faculty community and my own behalf, we welcome our guests and the participants across nation for today's webinar series. Welcome you, sir. Welcome the participants once again. Thank you very much for that opportunity given. Thank you. Over to Kalpana, ma'am.
Pleasant evening to one and all present here. It's my privilege in introducing our resource person, Professor P.Muthukumar, Department of Mechanical Engineering, IIT Guwahati. Professor has completed his undergraduation BE in Mechanical Engineering from University of Madras during the year 1996. He did his post-graduation ME in Mechanical Engineering with specialization in refrigeration and air conditioning from Coimbatore Institute of Technology during the year 1999. He received a PhD in Mechanical Engineering by completing his studies on metal hydride-based thermal devices for compression and storage of hydrogen from Indian Institute of Technology, Madras during the year 2004. Coming on to his professional experience, Professor has started his career in 2004 as a project officer under research in IIT Madras for 2 years. Later on, he joined at IIT Guwahati as an assistant professor in 2006 and became associate professor in 2010. And from 2016 onwards, he is continuing as a professor in IIT Guwahati. Sir is also having overseas professional experience under various positions like Scholar Exchange and also as a visiting faculty under DAT Fellowship in University of Stuttgart, Germany, as a visiting professor under Base Fellowship in University of South Florida, and also as a visiting professor under Fulbright Fellowship in Wichita State University, USA. Coming on to his publication, Sir has published nearly 96 papers as an outcome of his research in the areas like refrigeration, thermal energy storage, hydrogen energy storage and application, metal hydride-based thermal machines, sorption heating and cooling systems, porous medium combustion, etc. in SEI journals with Google Scholar citation of 2086, H index of 27 and I-10 index of 57. He has also published around 102 papers in reputed national and international conferences. In addition to his publication, he has also written chapters in books published by reputed publishers like Springer and Elsevier. He is the editor of various books and conference proceedings by Elsevier. He is also a reviewer of over 30 international journals. By adding feather on his crown, he has published 5 patents related to his research domain till 2018. He has delivered over 150 invited lectures in various engineering colleges, research institutes in India and abroad. Coming to his sponsored projects, Sir has completed a good number of consultancy and sponsored projects worth of rupees 560 lakhs funded by various funding agencies like DST, ONGCE, MNRE, PCRA, Robot Boss, etc. And also ongoing research projects worth of rupees 260 lakhs is in progress. He has guided 40 MTech students and produced 11 PhD graduates so far, and guiding 17 PhD scholars at IIT Guwahati currently. Regarding his awards and recognition, he has received DAT Research Fellowship 4 times. He is the recipient of IEI Young Engineer Award for the year 2010 in Mechanical Engineering from IEI. He is the recipient of Bhaskara Advanced Solar Energy Fellowship from Indo-US Science and Technology Forum. He represented India in Spain at Indo-Spain Joint Workshop on Renewable Energy. He received Young Engineer Award for the year 2012 from Senior Engineers Forum of Greater Guwahati. He also served as a president for ISRE Guwahati Sub-Chapter twice. He is the recipient of MP Baya National Award 2015 for Outstanding Mechanical Engineer by IEI Udaipur. He is the recipient of Mechanical Engineering Decide Award for 2017 from NDRF of IEI. He is also the recipient of Fulbright Nehru Academic and Professional Excellence Award for Teaching and Research for the year 2017 from US Indio Educational Forum. And his achievement journey continues. We are very fortunate to have such a wonderful resource person on day 1 of webinar series on research. In this occasion, I wish to thank our Principal, Dr. P.S. Srinivasan, Vice Principal, Dr. K. Vishagavel, Research Forum of KIOT, and Organizing Head for identifying and versatile personality, Professor P.Muthukumar, towards enriching our research knowledge. Dear participants, to get a good learnings out of this session, try to attend the session till the end. Thank you for the opportunity given. Thank you, one and all.
So now the session is turned out to our principal.
Yeah, thank you, Madam and Muniraj. Dear participants, I am very happy in welcoming you all once again. And I'll take just 3 minutes an introduction. See, today, the engineering education and the faculty dimension with which the faculty has to work all has changed significantly. Because of this, NBA going to be mandatory by the year 2022, and NAG is also becoming mandatory, and NIRF ranking has been introduced 5 years successfully. It is gone. Now there is a healthy competition among these institutions to do a quality work by all these things. So every institution try to move up in their quality chain and value chain. So that way, really every faculty now it has become a part of our faculty performance appraisal system, that minimum 2 research papers per year in a Scopus indexed quality journal is become mandatory. Otherwise, we cannot survive. That is a state of scenario that's coming up, and we also need to gear up. So in this connection, Knowledge Institute of Technology Trust has started this Knowledge Institute of Technology Engineering College and Knowledge Business School. It offers MBA program. And this trust is a unique trust. 22 engineering colleges faculty members who all have PhD and all have 20 to 30 years of experience have joined together 10 years back. And we put up one institute in Salem district where most of us belongs to. And our aim is make this KOT, Knowledge of Technology or Knowledge University, maybe in future, as one among the top 500 in the world ranking in 25 years. So in this journey, 10 years are over and another 15 years are there. And we have achieved reasonable distinction in Tamil Nadu state. So in terms of engineering admissions, we stand one among the top 50 across the state and top 20 in the western region, where about 200 colleges are there. And in Salem, Namakkal district, where we are located, one among the top two. So NB accredited, NAG accredited, autonomous we have applied, and we are because of this COVID committee did not we are expecting. So in this dimension, in order to sustain our quality journey, we need to do so. We thought of arranging a program for our own faculty. Then, because of this availability of such a technology like Zoom, we can reach throughout the globe. So that is the power. So why not we do this? So earlier we have done one five-day webinar series on NBA for Polytechnic faculty because desperately they don't know anything about it, and around 200 Polytechnic and 1,000 participants have attended across Tamil Nadu. And this we are not extended to other region because they wanted in bilingual. So another for all engineering college faculty also wanted a similar program, and we arranged on OB and NBA workshop. All these the webinars are available in our KOT YouTube channel, Info KOT. You can refer. That has got an overwhelming response of about 300 colleges and around 1,400 participants, and excellently it went on well. So from there, for this research also, faculty has request has come from various college faculty. So we have arranged this program, and in the meantime, few arts and science faculty has asked for certain quality enhancement programs, and we have arranged 3 such programs. And from that, there is a good number of arts and science faculty also there in that thing. So that is where there is a mix of this. Coming to specific to this program, this is being arranged. You need not know anything about research, but if you really attend these 8 talks, you can do a very quality research. The word we emphasize is a quality research. That is what is number 1. Number 2, so there's various stages are there. Because of want of time, I am cutting down because Muthukumar has got another meeting at 7 and he has to complete the session by 6:45. But how to identify a problem, how to approach a research, experimental, computation fluid dynamics. 2 more talks I have to add that will add on a MBA like streams or arts like streams, some survey based the research using statistical techniques. I'm in the process of fixing the resource person. So this 10 talks will complete a research on the entire spectrum of research methodology that is possible. The emphasis is on research methodology and the art of writing a good quality paper out of the research. So this is where the thing. Today's talk is a little more specific to mechanical and physics and chemistry related streams than other engineering streams. Similarly, talk number 3 will be more specific to fluid mechanics related topic and mechanical, civil, and environmental science, aeronautical, like that streams. But all other talks are general to anybody who wanted to research, to do a quality research. That is how we have structured. And coming to today's resource person, Dr. Muthukumar. So when I was doing my PhD at Kungu Engineering College, I had been to a conference at Science City Auditorium, Calcutta. And Muthukumar has come from IIT Madras. I don't know about him, he don't know about us. One Dr. Anjali Devi and his scholars have come from Bharatiyar University. We all happen to stay in a particular hotel where the organizers have arranged the hotel. That is where we met together. And since mine is heat transfer, he is also heat transfer man. The heat transfer team, we had a very good time for 3 days in the conference. And one day we roamed around Calcutta, that bridge and the Kali temple. We have a very good memory. From then onwards, we have a good association with Muthukumar. Incidentally, Dr. Muthukumar native is about 3-4 kilometers from our college. So whenever he comes in and he gives an invitation, either I go and meet him, either he or other he drops in and gives some talks like that. But in the last 2 years, since he has become extremely busy, that such things are not happening. At least today we are connected. And yes, hail from a very, very humble background, like agricultural family, rural interior. Yes, rise to great heights. To my knowledge, he is one of the very renowned experts in hydrogen energy storage across the globe. And don't think he does only high-end research. He has done some beautiful research in our everyday that gas burner, and yes, contributed a huge energy savings. That is LPG gas savings, and it is being commercialized and 3-4 now all burners mostly manufactured in India has got his research technology. So even to such fundamental level, we can do a research, not only the high-end research. That is the beauty of him. And another research person, Dr. Balakrishnan, he has started his career with CFT. He has developed his own CFT package, and all our DRDO laboratories use his package. And he has put up one startup company, and he is running the company for about the last 10 years successfully in ISC Bangalore. So how you can contribute, convert this research into yeah, your own business entity. From that perspective, we have added him. And to understand the second part, we need the first part. That is why the first part, though it is a little specific to mechanical, it is being there. Today, not only research and publishing, now we have to put patents and technology transfer. So that is where Muthukumar has done a technology transfer also. And Balakrishnan has got his own startup. And we are in the process of 3 products that we to technology transfer or our own manufacturing in the area of refrigeration and this ventilation. So like that, good number of things are possible. So with this overall perspective, but though don't think high end, you should not know anything about it. If you have a real interest in doing quality research, attend this 8-day plus 2 more talks, and the entire sphere of research methodology will have, and the art of writing quality research paper. And many of them do research and collect data, but put it in some nice graphs. But research and discussion is where the scholars struck. And if the guide is busy, then end up with a poor quality research. So my talk will be focusing on how to write any topic, not necessarily mechanical or electrical or physics, any topic. I have found out one. I have read some 2000 research papers, found out some one common methodology, and with which research and discussion can be beautifully done. So that is what you will get out of this. Every webinar we will give a link. This because dates are not finalized, so we could not able to generate one link. In the forthcoming talks, you can also request many of your colleagues also to join. YouTube also you can view at any point of time. You can see live also. So like-minded people, whether they talk or they do not, they united by heart and mind. So that is how my connection with Muthukumar is there. He is so busy, he could not able to really allot time. That's why we have postponed this to today. And, and Dr. Jayvel is, I don't want to take much time now. He's excellent. He has got some 42 is his H index, and citations are enormous. And his nanotechnology is one of the world-renowned person. So like that, beautiful people are there, and they will make the lectures not to their level, to the beginner level. So with this note, I'm happy that Muthukumar able to find a time. And one more talk, he has to give a date and time. That is a more general talk on research methodology. So I think so many people have come joined in Zoom also, and YouTube also. So that shows you are all ready to do a quality research in India. And one more word, my dear faculty members. This COVID, this China, worldwide China and other country relationships are making a larger shift towards Indian engineering industry. And 1.5 years down the line, you see another 10 years, we will have an exponential growth in engineering and technology, both in terms of manpower requirement, both in terms of R&D, and if you equip now with the quality research and design mind, then you will be the hot cake. Maybe today the situation may be dull. Don't think that. I foresee that. I will talk about that in my talk a little bit more. With this introductory note, I request Muthukumar to take over the session. He will cover about the very basic thing. If you do an experimental research, there is no proper textbook or guidance available to on major areas. So don't think that is limited to pressure, temperature alone. Any branch of engineering, anything you do, so methodology will be the similar, approach will be similar. Only instead of pressure, something else, instead of temperature, something else may be there. So how to select, how to calibrate, and how to install that embedding in the external facility itself creates a lot of errors, and you have to take extraordinary care in terms of getting precision outcome. And calibration is a tedious job. And with all those things, finally, what is the estimated uncertainty in the final results? It has to be plus or minus 5 to 10%, not more than that. So how to achieve that? So these are all the topics he will be covering. But he said every topic you put requires 3 hours of my time. But I don't know how to do justice. Anyway, I said, sir, people, once you create an interest, they will automatically tend to learn more. So I request Muthukumar to cover as much as you can possible, or otherwise, some maybe after a month or so, if you can have one more talk. And wherever not possible, you can refer, which you go and see this, you will get some good quality outcome, maybe a video or a research paper or something else. With this introductory note, I welcome Muthukumar to take over the session. Over to Dr. Muthukumar. Thank you, my dear friend.
So am I visible now?
Yes, sir. It's visible.
Yeah. Okay. So good evening, everyone. So first, at the outside, I would like to thank Professor Srinivasan, of course, my close friend, for arranging this talk. And also, I thank Dr. Kalpana Devi for the friendly introduction. So hope all you are set to listen to me. So basically, in this talk, I will be discussing about the three important quantity measurements, that is temperature, flow, and pressure. Because these three measurements are, of course, related in a way. It's related to our day-to-day life. So that's why, in fact, I have chosen these three measurements. And besides that, and we also see the the experimental uncertainty analysis and the selection of instruments and sensors, and also we can also see the design of experiments. Anyway, I will try my level best to cover all the major topics. Again, the time is the constraint. And beyond, of course, if I stretch my lecture beyond 90 minutes, it may also boring for you. Anyway, I try my level best to keep you engaged. So before going to the topic, I wanted to give you a brief introduction about our institute. It's IIT Guwahati. It's located in Guwahati, which is the gateway of the 7 northeastern states of India. Our institute is established in 1995 and of course started in 1995 and well established during 2005. Currently, we have 7 engineering and about 8 engineering, about 4 science, and there are about 5 to 6 centers. And our current student is nearly about 7,000, and we have about approximately 500 faculties and about 500 plus non-teaching faculties. And in addition to that, we also have a few thousand number of migratory birds, wildcats, and jackals, and etc. So we are the third cleanest campus in India, and beautiful among other IITs. In the background, you can see the Brahmaputra River here. And this is our academic campus. So during the raining time, so without getting wet, one can access any, of course, building. That's how it is designed. And so these are our interior part. So it's a kind of evergreen campus, and we are spending a lot of money for beautification as well. Okay, so coming to the our the main, of course, the business. The measurements. So why we need measure and why do we measure the things? So basically the measurement is, it's very basic for estimating the amount of something, and measurement is very basic for any R&D and innovation related activities, and it's also of course necessary for the controlling the process or monitoring any process. And to establish and enforce standard, we need measurement. And if you want to share any technical information on any technical resource, of course, we can share only in terms of measurement. Without that, we cannot measure. And suppose you are developing some kind of a numerical scheme or numerical tool. So to ensure the reliability of the numerical scheme, we need validation. It can be done via only measurements. So therefore, of course, in any R&D related activities, the measurement is very, very essential. So in this talk, basically, I will try to cover the basics of temperature, flow, and pressure measurements. And we also see the uncertainty analysis. Then at the end, of course, I will highlight about the selection and calibration of various instruments, and obviously we'll see the application of various instruments. So if there is any connection disturbance, please do inform me. Since it is an online talk, so I cannot get any feedback. So if there is any disturbance, please do let me know.
Sure, sir.
Okay, so the coming to the standard, of course, one must know the standard. This basically the standard provides the reference for any measurement. Basically, you take any quantity, whether it's a temperature, pressure, or mass, or length, whatever may be this one. So everything is measured with the reference to a standard. If you take a temperature, 0 degree. 0 degree is the standard for it's a standard set by the water, because water at atmospheric condition, it freezes at 0 degree. So considering that standard, 0 is defined. Similarly, 100 degree. So water at atmospheric, condition, water boils at 100 degrees. So based on the boiling point of water, the 100 degrees, of course, the referred. So likewise, we have the other quantity. So therefore, whatever the standard you are defining, it should be internationally accepted, and it should be demonstratable. And basically, the standards are defined based on some physical or natural phenomena, or based on some arbitrary the material standard, which includes some physical constant, etc. So anyway, I don't want to discuss all these things. These are the basics, so one can find in the open literature. So basically, any instruments, when you talk about the ideal instruments, obviously the first the thing will come into the mind is the cost, because India is a developing countries. We cannot afford for a highly sophisticated, of course, the expensive instruments. So therefore, for Indian researchers, the cost, of course, plays a major role. And of course, we have to see its reliability. Then sensitivity, even the instruments should be in a position to detect the small change in the input. So therefore, we prefer high sensitivity, and accuracy also reasonable. And the instrument should not get affected by the surrounding environment. Sometimes if the moisture, of course, goes high, the instruments, of course, it may not perform. So that you have to take care. In sometimes the magnetic field and the other electromagnetic field also may affect the instrument's performance. So therefore, the instrument should be free from all this disturbance. And the operating range, again, it's a questionable. If you want to have a higher operating range, then you need to, of course, compromise with the accuracy. So that, of course, based on your application, it will vary. Then possibly the instruments should give the direct, of course, value. It should give the direct measurement. Like, for example, if you take the thermocouple cannot give the direct temperature output. Basically, the output of thermocouple is voltage. Again, we need to have a conversion from voltage to respective temperature. Similarly, you can see the mass flow meter, pressure sensor, and all these things. All the devices, provide the output in terms of either milliamps or millivolts. So again, we need to have a conversion. So unlike these instruments, the ideal instrument should give the direct, of course, display. And the instrument also should have the interfacing facilities for the temporary storage or the long time, of course, process. So these are the ideal requirement of an instrument. Okay. So then before going into the instruments, one should also know about the calibration. So calibration is nothing but it's just you apply the known value of input and find out the instrument's response. That is nothing but the calibration. So basically, it's a process of determining the relationship between the instruments, of course, the output and the standard value. So I have given a very simple example. It's a simple bring balance. So here we are applying the known weight, and then we are finding the the deflection. That is the deflection observed from the spring. So we need to have a kind of a relationship between the, of course, the known input, which is nothing but the standard mass, and with respect to each standard mass, then what could be the deflection. So you need to establish a relationship. Basically, this relationship provides you the calibration scale. So based on this relationship, you can see there is a scale, marked scale. This scale is defined. So before going to any, before going to use of any instruments, so you need to calibrate whether we need to know. So from the calibration only, we can find out whether the instrument is, of course, providing the actual results or not. The actual value or not. So this then next one is the the static characteristic. Basically, the instruments have two types of characteristics. One is the static characteristics, which is of course often called as performance rating of an instrument. Another is a dynamic characteristics. Actually, these dynamic characteristics, it's mostly related to the dynamic nature of input or the response of the first order or the second order instruments. So coming to the dynamic, the static characteristics, I think the most of you familiar about this term, like accuracy, precision, sensitivity, and zero error, linearity, hysteresis, repeatability, reproducibility, and drift, and etc. Anyway, this one can refer in the standard textbook. I don't want to spend time on this. So mainly just I wanted to highlight 2 points here, the accuracy, because many times people often, of course, get confused with this terminology. That's why I wanted to give you a clear-cut idea about it. Basically, accuracy is nothing but it's a difference between the measured value and the true value. True value is nothing but the standard. Okay, this difference gives the accuracy. So usually, if you choose any instruments, the accuracy will be defined in terms of this full scale reading, which is nothing but the the difference between the measured value and the true value divided by the maximum scale value. For example, in case if you take the pressure sensor, the difference between the measured value and the actual values, let us take pi, Pascal, and the maximum scale volume is, let us take 1000 Pascal. So pi divided by 1000 multiplied by 100. This is the accuracy. Okay. So usually it will be expressed in terms of plus or minus some percentage. Then coming to the precision. So precision is nothing but the instrument should be in a position to produce the same value of output for a given input, given in of course given in various point of time. So see, whenever you give the same input, the instrument should give the same output. Okay. So suppose the instrument is free from the random error, then only of course it can produce the same value. If it is having some kind of a random error and it cannot produce the same value for the same for the given same input. So this is very important. And so now we will of course move on to the temperature measurement. So as you know, basically temperature is the measure of hotness or coldness of your body. So basically there is no instruments, of course. There is no way you can directly measure the temperature. Basically, the temperature measurement is done by observing the change in temperature dependent property. For example, by observing the change in electrical property, you can measure the temperature, or by change in physical property, you can measure the temperature, or change in chemical property, or change in for observing the the amount of radiation received from the body, you can measure the temperature. So therefore, in temperature measurement, we don't have any direct comparison. So most of the measurements are done by indirect comparison. So here the temperature scales, the commonly used temperature scales are like Fahrenheit, Celsius, and Kelvin, and there are the relationship. And so basically, here the temperature scales are established based on the physical and thermophysical property of some substance. And so before going to the temperature measurement, of course, everyone should know about the zeroth law of thermodynamics, which is the basics for temperature measurement. And here also, of course, the most of the people, of course, have some kind of a misinterpretation in this law. So basically, this law says that if you consider the two body A and B, and if these two bodies are thermal equilibrium in each other, and the third body and the body B is in thermal the body B is in thermal equilibrium with the body C independently, then the body A and C are in thermal equilibrium. So this is the law. Basically, this is the basics for temperature measurement. Just I will give an example. Maybe if you take a class in Mercury Thermometer, and if you are going to measure the temperature of your water, is kept in a class. So here, you can treat the thermometer is a body A, and the body B is your water. And then someone can ask, where is the body C? The body C is physically not present. So here the body C is the standard. So basically the thermometer is calibrated based on the standard. For applying the different standard input, for example, 0 degree, 50 degree, or 100 degree, based on for applying the standard input, the first the thermometer is calibrated. So initially the thermometer is made thermal equilibrium with the standard for calibrating the scale. So now the thermometer is immersed in the body B, that is your water, and when they were in physically in thermal equilibrium, then it provides the reading. So that reading is established by a standard. Okay, so this is the thing. So don't of course misinterpret. And okay, fine. So now we will see the temperature measurement, and basically there are four ways you can measure the temperature: by observing the the change in physical property of the material, by observing the change in chemical property of the material, or by observing the change in electrical property of the material, and the fourth one is by observing the radiation received from the body. So in this way the temperature can be measured. So quickly we will see in each category. First we will see the physical change in physical property. Here is the biometallic thermometer. This is a very standard temperature measuring device. It's widely used now. It's mostly used in the process controlled areas. So basically this thermometer consists of two this metallic strip of having these different thermal expansion coefficients. These metallic strips are of course binded together by using a temperature you can say the high thermal conductivity cement. And when this strip is exposed to the unknown temperature, because of their difference in thermal expansion coefficient, and they will bend. They will bend. So this bending movement is transferred to the needle, which is moving over the calibrated scale. So by measuring the deflection of the this metallic strip, the unknown temperature can be measured. So the examples are like the SS, brass, or copper. These are the high metallic strip. And now you can see here in the photograph. And so the range can be based on the material configuration. The range can be anywhere between -65 to 430 degrees Celsius. And accuracy, you can get the better accuracy as close as 0.5 degrees Celsius plus or minus 0.5 degrees Celsius. And advantage, these are very low cost, and this reliability of this instrument is very good, and it can work for over a long period of time. Once you calibrate this instrument carefully, then you don't need any kind of further calibration. Basically here the drift is almost zero. So the application is in a thermal cutoff relay. Maybe I think most of you are aware that in your iron box, when the temperature reaches the particular value, you can see the power will cut off. So this is the ideal application of this instrument it's used in the iron box, and there are many control ELOs it is used. And and the next one is class in mercury thermometer. So here the temperature is measured by observing the rise in mercury level in a capillary tube. So basically you see here in the capillary tube the thermometric fluid is filled, and then when you are measuring the temperature, basically you need to immerse this capillary bulb inside the medium, and then heat will transfer from the medium to the bulb. Because of the heat transfer, the fluid will expand. Then it will flow over a small capillary, which is of course fitted over the calibrated scale. So then directly you can see the temperature. So basically the class in mercury thermometer, it's a very standard one, and it can be used anywhere between -37 degrees Celsius to about 400 degrees Celsius. That's the ideal usage. And so here one thing I wanted to tell you here, basically these thermometers are calibrated in three ways. One is the partial immersion, second is the total immersion, and third one is the complete immersion. Partial immersion means if you see the thermometer and the bulb, above the bulb you can see a marking, that is a red color marking. So actually that marking is done for a reason. So whenever you are measuring the temperature, you have to immerse the thermometer till this marking. Then only you will get the accuracy. Suppose if you immerse it full or maybe immerse it partially, then you will end up with having an error. And then sometimes in some thermocouple, especially meant for the high precision application, there will not be any marking. In that case, you have to insert the thermometer till the mercury level. Okay, carefully you have to insert the thermometer till the mercury level. That is called the total immersion. And the complete immersion, of course, we are not using it. In the complete immersion, you need to use it for the it's mainly used for the atmospheric temperature, but nowadays nobody is using the complete immersion. But in the thermometer, class in mercury thermometer, you will find these two type of calibration one. So if you use it and if you wrongly use, then you will end up with the error. So this error, even in the real time, can be also estimated, and there are equations available for estimating the error. So coming to this, of course, this is again this mercury class in thermometer is again meant for measuring the static temperature measurement. That means it can give only the steady state temperature. Suppose the temperature is varying with respect to time, then it cannot, of course, measure. Basically, the time constant of these thermometers are very high. So the next version is, of course, the constant, the vapor pressure thermometer, you can say. So basically, in the vapor pressure thermometer, there is a small bulb and of having very precisely measured volume. This bulb is connected to a pressure measuring device, which can be a simple manometer, or maybe a transducer, or maybe a Bourdon tube pressure gauge. And so when you keep this bulb in an unknown temperature medium, and because of the heat transfer, the gas which is filled in the bulb will expand, will create a pressure. So this pressure can be measured either by using a simple manometer or maybe a pressure sensor. So from the pressure, then you can measure the temperature. So here we need to have a very precise calibration between the pressure and the temperature. So here the temperature range anywhere between -152, you can go up to about 500 odd degrees Celsius. Here the high response can be obtained, by having a shorter length capillary. If the length the capillary is too large, then the response, of course, will be slower. So this you can see here there is a typical example here. So here the capillaries, you can see, directly connected to a needle through some kind of a spring arrangement. So as soon as if you apply the heat to the bulb, the gas will expand. The expansion will be given to the another capillary, which is controlled by a spring. So then because of this expansion will be transferred to the spring, and where the needle is attached. So the needle will move over a calibrated scale. Then you can find the temperature. So this is about the pressure thermometer. And so the advantages are basically for both the the thermometer, this glass and mercury thermometer, bimetallic thermometer, the pressure thermometer. These all are the passive type instruments. It does not require the external power to operation, and they provide stable in operation. Only thing is these instruments are meant for the steady state temperature measurement. If your quantity is varying with respect to time, of course you cannot use it. And again, the remote location also, it's difficult. But if you have a long capillary, you can also go for a remote sensor. This is actually typically used in our air conditioning equipment or many applications. You can find this sensor. So the next one is this is a more versatile, this sensor, RTD, temperature resistance device. Detector, you can say. Basically, if you take a tungsten wire, if you increase the temperature of the tungsten wire, its resistance will increase. By measuring the increase in resistance, you can measure the temperature. So the correlation is given here. So the resistance at any given temperature R is equal to reference resistance at room temperature. Then IA, this is the calibration coefficient, times T minus T reference, where T is the unknown temperature, T reference is a room temperature or maybe 0 degrees Celsius. So when you expose this RTD, when you place the RTD in an unknown temperature, its resistance will increase. By measuring the increase in resistance, you can get the temperature. So of course, instead of RTD, one can also use you can say the nickel. Usually the RTD is basically it's a PT100. The platinum, this one, because the platinum will have a resistance of 100 ohm at 0 degree. That's why it's called as a PT100. We can also use copper or the nickel or any metal you can use. And so basically, if you take platinum, and it is having very linear characteristics, anywhere between -200 degrees Celsius to up to about 1000 degrees Celsius. It's a more suitable. And copper is having some kind of issue linearity issue. But nickel, you see here, their slopes are different. So the RTD basically, having the wide operating range, as I already mentioned, it can be used between -252, to about 1000 degrees Celsius. Highly sensitive and much better than the thermocouple. And accuracy is also here, you will get plus or minus even 0.05 degrees Celsius, which is highly impossible in case of the thermocouple or thermistor. And reliability and repeatability, even if you use it maybe about 10 to 15 years, its characteristics not going to change. Only thing is, in case of the RTD, it's very small, thin kind of a film. It's very fragile in nature. When you are handling it, you have to be very careful. And from the this one, the this film, we need to take the output. So therefore, we need to have a lead wire. Sometimes the lead wire will have some kind of a additional resistance that, of course, you need to take. This can be done by proper calibration. These are all the issues associated with the RTD. But in general, for most of the R&D purpose, we use the RTD for the temperature measurement anywhere between -200 to about 1000 degrees Celsius. Now coming to this one, thermistor, this characteristics is just opposite to the RTD. In case of the RTD, the resistance is directly proportional to temperature, whereas thermistor, the resistance is inversely proportional to the temperature. Okay, that means if you increase the temperature, the resistance will go down. So again, by measuring the change in resistance, temperature can be measured in the thermistor. Basically, thermistor, these are the semiconductor material and mostly made up of ceramic, type or silicon type semiconductor. And so here, if you see the accuracy, again, you will get the better accuracy. In fact, much better than in RTD, and even better, much better than the thermocouple. And sensitivity is very better, very high. Here, you can see the time constant. The time constant will be in the order of about microseconds to milliseconds. It's a very fast you will get. And the problem is these thermistors are limited, in a shorter, range. For example, if you want to measure the thermistor, say if your temperature range is say from 0 to 200 degrees Celsius, the same thermistor cannot fulfill your purpose. Maybe for 0 to 30, you have to use one thermistor. From 30 to 100, you have to use another thermistor. And again, 100 to 200, you have to use another thermistor. So all the thermistors are having very narrow range. That's the only problem. And so, of course, according to your application, precisely you have to select the thermistor. So now here you can see here, there is a direct comparison between the thermistor, thermocouple, and RTD. And the thermocouple, basically, again, the thermocouple also, with respect to temperature, is having increase in resistance. RTD, almost like linear relationship, whereas we get thermistor, it is inversely proportional, this one. But most of the thermistors are not having linear relationship with temperature. Maybe to some range, there will be linear, and again, there will be a flat, and there will be a different this one. So therefore, according to your range, you have to select the thermistor. Okay, now we will move on to the thermocouple. Basically, the thermocouples, these are the most commonly used, passive type, you can say, the sensor. It's basically, it's not like an instrument, it's a simple wire, just similar to the electrical wire. Basically, this thermocouple works based on Seebeck effect. So we have to take two dissimilar metals, and then you form a junction. And when these two junctions are maintained at different temperature, there will be a EMF induced in the circuit. This induced EMF is directly proportional to the temperature difference between the two junctions. So usually the one junction is kept at 0 degree. It's a reference point. Another junction will be at unknown temperature. So therefore the induced voltage will be directly, proportional to your unknown temperature. Here, one thing I wanted to tell you that, so whenever you are measuring the using the thermocouple, your circuit should be open. Okay. So if you close the circuit and there will be a flow of current, then once the current flow taking place, then instead of Seebeck effect, then you will end up with having Peltier effect. Then instead of measuring, the voltage, then you will end up with producing the cooling effect. So it should not be done. Usually, whenever you use a thermocouple, either you can go for a data logger, or you can go, if you don't have the data logger, you have to use the high resistance potentiometer. Okay. So the potentiometer will have the high resistance, therefore it won't allow the current to flow. So this, of course, you have to take. And here there is a point, whenever you talk about thermocouple, it should be dissimilar metal. There is a difference between different metal or dissimilar metal. Different metal means it can be any two metals, like it may be copper or iron or this one, or magnesium or anything. Whereas dissimilar metal is, if you based on the the valence electron at the outer orbit, the metal can be classified as positive metals and negative metals. So for forming a thermocouple, we need one positive metal and one negative metal. So you cannot form a thermocouple by using two negative metal or two positive metal. This, of course, you must remember. So here is the circuit, And as I told, and here there are two dissimilar metal, copper and then Constantine. Copper is a positive one, Constantine is a negative one. So you, with the help of these two metallic wire, you form two junction. So one junction is maintained at the reference point, which is normally at 0 degree, and another is unknown temperature. So when you connect this thermocouple, and then EMF will be generated, this EMF is directly proportional to the temperature difference between these two junctions. And also it is depends on the material property. That means the whether it is what type of thermocouple. Okay. So basically thermocouples are they are inexpensive. Like if you take 1 meter wire thermocouple wire, it hardly of course varies from 40 to 50 rupees. And if you buy in a bulk quantity, even you can get at 30-35 rupees. So that is a T-type thermocouple, and even the R-type thermocouples are a little expensive, which may cost around few thousand rupees. Okay, so just I wanted to, since we discussed about the CFEC effect, and I wanted to tell you, if the circuit is closed, then what will happen? That is your Peltier effect. Suppose if the circuit is closed and you will end up with having a current flow, and because of the current flow, one end will be experience cooling and another end will experience heating. So this basically, this is the concept of thermoelectric cooling, and which is used in the for producing the cooling effect. And here is the definition difference. You see here, the circuit is open and you will have a CFEC effect, which is meant for generating the voltage. You can say the power generation. The circuit is closed, then the resultant the circuit will become the Peltier effect, which is of course used for cooling application. Okay. So as I already mentioned, the thermocouple should have two dissimilar metal. One should be a positive metal, another should be a negative metal. And how the thermocouple is named? Basically, it is named after the two materials. The first one will be the positive metal, and the second one will be the negative metal. So like you take the copper Constantine. So here the copper is the positive and the Constantine is negative. So this is the D-type thermocouple. And now here you can see here the different positive and negative metals. Basically, by combining these two things, you can make a thermocouple. So basically, the thermocouples are tailor-made. I can say according to your specification, you can make your own thermocouple. Only thing is, the concern is that your thermocouple should have one positive and one negative metal. So this is very important. With that, of course, you can go for it. So now, after making the thermocouple, there is a standard procedure for joining these two wires. Just like that, you cannot join. So when you join this wire, you need to follow certain things. And so, of course, there are the way after joining this thermocouple, you have to make a twist. Twist it, and carefully you have to join by using the inert welding, inert gas welding. So basically, when you are welding this two wire, you make sure that there should not be any oxide formation over the bead. If there is oxide formation, then you will end up with wrong reading. So when you are going for the industrial use, basically the bead will be, of course, covered by the enclosure. So if you want to have a fast and rapid sensitivity, the bead should be exposed. Okay, it should you could see the bead physically. So then only it will give the better sensitivity. The rapid sensing. Basically, if this the bead is exposed to the environment, it will have, because of the better heat transfer characteristics, it will give the rapid sensing. And sometimes because of the chemical hazards and other operational issues, you may require to protect the bead. So therefore, you need to have an insulation. That is the insulated junction. Mostly the insulated junction thermocouple will be used in the furnace, because in the furnace are experienced at high temperature, and there will be a lot of flue gas and ash and etc. Many things will be there. Therefore, you need to protect it. So based on your the sensing requirement, you can opt for either bare-ended thermocouple or insulation-ended thermocouple or grounded thermocouple. So whenever you go for the temperature measurement where the electrical circuit interference is there, you must go for the grounded junction. In case of the grounded junction, the inside this capsule, you fill with the magnesium oxide powder, because the magnesium oxide powder is having very good thermal conductivity, but electrically it is an insulator. Okay. So these are the class of thermocouple. This you can find it in any textbook, like E, J, K, T, R, and X, and etc. Each thermocouple has its own temperature range. You can see the respective temperature range. Suppose if you are looking for the low temperature measurement, say from -50 to about a few hundred degrees Celsius, the T-type thermocouple is the best one. which is having a very good accuracy, and K-type thermocouple is essentially meant for high temperature application. If you want to measure the temperature above say 200 to up to 1000 degrees Celsius, you opt for the K-type thermocouple. Suppose if you use the K-type thermocouple for low temperature application, the error will be very high. You will end up with having more than 5 degrees Celsius. And the J-type thermocouple is again, it's meant for 0 to 200. But there is a problem with J-type thermocouple. Whenever if there is any wetty environment, or if you are going to if you are going to measure the temperature in a water medium or where the presence of liquid, please don't use J-type thermocouple. In presence of water or moisture, J-type thermocouple will generate additional galvanic EMF, which will lead to error. And again, K-type thermocouple is not advisable to use where the the environment is having high vibration and noise. So that cannot be used. And then chromal type thermocouple, it's a very highly sensitive. But the problem with E-type thermocouple is it needs periodic calibration. And R and S and B type thermocouple, these thermocouples are very expensive. If you are going for temperature measurement above 1000 degrees Celsius, then you prefer R or S or B type thermocouple. Okay. So here you can see whatever the things I have seen shown there. This is basically temperature versus the voltage. This is basically it's a characteristics. I mean, you can say the characteristic. Among this, you can see the E-type thermocouple is having, of course, the high sensitivity. Okay. So yeah, so you need to have some special precaution. This which I have told you. So J-type thermocouple cannot be used in presence of water, and K-type thermocouple cannot be used in presence of noise or vibration. And when you are going for electrical interference, then your thermocouple should be grounded. And basically, then you need to go for better electrical ground. You can go for the magnesium oxide filling. And so suppose sometimes you may require to measure the temperature difference of very small magnitude. For example, if you want to measure the delta T of maybe about 1 or 2 degrees Celsius, if you use a thermocouple, the thermocouple may not sense because the temperature difference is very small. So sometimes even if you use a thermocouple and because of the small delta T, you will end up with more error. In such case, you can go for the thermopile. Basically, thermopile is the combination of same kind of a thermocouple. Here you need to connect thermocouple of either it is a T or K. You have to connect them in series. Okay, you see here. So maybe if you in this particular figure, I made 3, of course, the the junctions. 3 junction in the T2 and 3 junction in the T1. So therefore, whatever the output comes out from this net circuit will be the 3 times of the actual output. So that here, what is happening? The voltage is getting multiplied. So therefore, you can minimize the error. So basically, this thermopile circuit is used in IR thermometer. Okay, that of course I will explain you the later slide. So now if you want to measure high temperature, like in the order of about, already we have seen like R and S and B type thermocouple can be used up to about 1700 degrees Celsius. If the temperature is above 1700, maybe say up to about 2500 or 2000, actually which sometimes this kind of temperature measurement is required in the furnace or the melting in a system. So here we can use the boron and graphite thermocouple, but these thermocouples are very expensive. Okay, rhodium and rhenium type thermocouple, these are very expensive. But still, if you want to go for the better or maybe cheaper option, yes, we can go for, there is a option is available, that is the pulse cooling thermocouple. Here, by using symbol or K or R type thermocouple, you can measure the temperature in the order of about 200 to 300, 2000 to 3000 degrees Celsius. Let's see how it can be done. So basically here you can take either K-type thermocouple or R-type thermocouple. You enclose them in a small enclosure. You keep them in a small enclosure. And so what you can do, normally this thermocouple will be cooled by supplying the normal air. So whenever you need the temperature measurement, you close the normal cooling air and supply the hot gas, which may be above 2000 or 3000 degrees Celsius. Just to supply it, and you maybe supply only maybe about few seconds. And within the few seconds, and measure the thermocouple response. That means increase in temperature of the thermocouple. Then maybe you shut up the the flow. Then by measuring the temperature response of the thermocouple, by knowing the time constant, then you can get the the actual temperature by using the relationship, that is tau is equal to, that is the change in temperature with respect to time, and what is the increase in temperature maybe within about few seconds or few odd seconds that you will be getting in actual case, and multiplied by the time constant, then plus the temperature, of the thermocouple measured at the end of the few seconds. That summation gives you the actual temperature of the gas. So this is by using a simple technique, you can measure it. And so these are the heavy duty, thermocouples. It's meant for industrial application. The last one you can see here, this is basically it's a sheath, sheath. Particularly when you go for the temperature measurement in the high environment, the high corrosive environment, we need to protect the bead. So by using this kind of a production, we can do the temperature measurement. So these are the special type of rapid sensing thermocouple, of course, developed in our institute. This is mainly meant for temperature measurement in a high, high reaction rate chemical reaction. So you can use this kind of thermocouple. These thermocouple sensitivities, I mean, the time constant is it's less than, you can say, the maybe about milliseconds. So one should know about the codes. These are the commonly available codes for representing the thermocouples. So basically, we follow the French code, like I mean, from here, I mean, you can see the fourth column. That means the K-type thermocouple is yellow, and T-type thermocouple is blue, and E-type is in pink color, and J-type is in the, of course, the ash color. Basically we follow the French, designation. And again, this is the summary of all the, the temperature measurement. Anyway, this I will skip it, and this also will skip it. So coming to the calibration of the thermocouple, so this is very much important. So as soon as when you purchase the thermocouple, after making the thermocouple, you should not, of course, use the thermocouple directly. Before going to use, you must calibrate. So how we can calibrate? So for calibration, of course, there are standard, standard constant temperature baths are available, or maybe you can also go for the, dry, blocks. These are available in the market. When the constant temperature bath, you can set the temperature. Maybe you can set the temperature maybe at 0 degree or 30 degree or 100 degree or 200 degree. You can set the temperature. But when you go for the calibration, you make sure that your temperature bath is having high accuracy. At least here the accuracy, the error should be within maybe plus or minus 0.1 degree Celsius. And the bath also should have very good temperature stability. That means wherever you measure the temperature, it should give the uniform value. So first you set the temperature maybe at 0 degree, and then you see the thermocouple response, whether it is showing 0 or not. And then slightly for every 10 degree, you have to go. I mean, you have to increase. And then you make a kind of a plot between your thermocouple, the standard input. Standard input means that is the input set by the, from the thermostatic path, and the output of the thermocouple. So you make a, present the characteristics. And then from the characteristics, then you can get this equation. That is the T actual is equal to A plus B into B into TD and C into D squared. TD is the, of course, the temperature which is shown by the thermocouple. So with this, of course, the calibration, of course, if there is any error, so you can, of course, rectify error. So this is very much essential. So any device, any sensor, if you purchase, of course, you must go for the calibration. So for even the companies also provide the calibration chart, but that may not be accurate. You must do your calibration according to your experimental condition. And third one is the temperature measurement by observing the change in chemical property. And so there are some kind of liquid crystals which is having mechanical properties, and also it is having the optical properties. So basically, when this crystal, this kind of the crystal liquid crystal, when they expose to different temperature, its color will change. By observing the change in color, of course, you can measure the temperature. Of course, here there is an issue. You cannot get the better resolution. Even accuracy also very poor. But this type of techniques gives you some kind of the first-hand information. For example, usually if you go to a thermal power plant or any power industry, some of the heat exchanger will be painted with this thermal detecting paint. So usually they will be in kind of yellow color. When the temperature goes beyond the safety level, then the yellow will become red. So by observing the color, so they can come to know that of course something is going wrong. So this will give the first-hand information. Even if you go to the the foreign countries like US and this one, so they use for measuring the body temperature, they will give some kind of a small strip. So we have to keep this strip in our mouth, and then after some time, then the color will change. So that will give the indication. So this is for the medical use. and many such kind of things are available. So now the another the interesting application is how to measure the temperature in a high speed stream. For example, let us assume the stream is flowing at a velocity of say about 10 meters per second. You want to measure the temperature. You cannot keep a simple thermocouple over there and measure the temperature. What will happen if we keep any thermocouple on any temperature measuring device in the presence of high speed steam? What will happen? Basically when you introduce any object or obstruction, within the vicinity of the obstruction, the flow will become stagnant, because the flow will be adiabatically, it will be it will become rest. So therefore, when the flow becomes stagnant, the kinetic energy that is which is associated with the velocity of the fluid will be converted into local enthalpy. So it will give the temperature rise. That means whatever the temperature you are sensing from your temperature measuring device, it may not be accurate. So how do you find that? So there is a relationship. So the stagnation temperature of any stream can be measured by, and find out can be by using this equation: T naught is equal to T infinity plus V square by 2Cp. In terms of Mach number, we can get this standard relationship. But what will happen? So in the actual case, the temperature measured by the sensor may not be equal to the stagnation temperature. If it is a stagnation temperature, so with the help of this equation, you can get it, but it may not be equal to the stagnation temperature. But it is also, it will be definitely higher than the actual temperature. So whatever the temperature measured by the temperature sensor, that will be your recovery temperature. Excuse me, just a minute. So this kind of temperature sensor, of course, will come with a very special enclosure, where the this recovery factor, that is R, that is nothing but the actual temperature drop divided by the ideal temperature drop, which is nothing but the T naught minus T infinity, that is the ideal temperature rise. Then in the numerator we have the actual temperature rise, that is TR minus T infinity, where TR is the temperature recorded by the sensor, where R is the recovery factor. Basically, the recovery factor is, it's a design parameter. So for a given the sensor, you can estimate the recovery factor by knowing the recovery factor. With this help of this one, by knowing the recovery factor, the temperature of the actual case, that is the T infinity, can be measured from the value of T stagnation and as well as the TR. So this is very important. So whenever you are measuring the temperature of your high speed steam, so you must understand that the temperature what you are getting from the instruments may not be the correct value. So you must taken care of this stagnation one. So this is the special type of the sensor designed for the temperature measurement in high speed steam. You see here. So now in the above graph, you can see here the error. I mean, the rise in temperature with respect to Mach number. So the Mach number is in the order of say 0.8. You see here the rise in temperature will be approximately equal to 30 degrees Celsius. If it is a Mach number is 1, the rise in temperature is more than 50 degrees Celsius. So these aspects, of course, you must take into account. So the last one is the radiation method. So here basically the temperature is measured based on the radiation. Radiation, it's a electromagnetic propagation. So by focusing the radiation emitted from the body to a black body or maybe a photon detector, then you can measure the temperature by using the fundamental law of radiation. Of course, here we have the radiation pyrometer or optical pyrometer, bolometer, and IR thermometer. There are several versions we will see. So basically, in the in radiation pyrometer, so basically the radiation received received from the body will be focused to a small point, which may be in black in color, because the black body will receive radiation from all wavelength, and which is the ideal one. So there are two things. So in the black body, you can have a symbol thermocouple or maybe thermistor. This will provide the rise in temperature. From the rise in temperature, the unknown temperature body can be calculated. Or instead of a black body, we can also have a small photon detector, which will produce the electricity by receiving the radiation, which will produce the EMF, that is the electrical charge. By measuring the electrical charge, the unknown temperature can be measured. These are the very simple way. So in case of the photon detector, I mean the temperature one, so we need to wait, when the radiation, when you receive the radiation over a black body, its temperature will increase. It will increase till a point where the heat received from the unknown body will be equal to the heat loss to the surroundings by either by conduction or convection or radiation. Under the thermal equilibrium, you can measure the temperature of the black body. From the temperature, you can get the temperature of the unknown body. So the relationship is very simple. So sigma into T to the power 4 is a Stephen Boltzmann law. If it is a real body, then the emissivity you have to take into account. That is equal to K. K is the constant. This is the photo of the black body constant. Well, T2 minus T3 is the temperature rise. By measuring the temperature rise, the unknown temperature T1 can be estimated. It's a very simple one. And then the polometer, basically polometer is polometer. When you focus the radiation to this device, it will generate electricity. This can be a simple thermistor or maybe a thin film of metallic film. So this will basically, it will produce the thermal output. So by measuring, the electrical output, by measuring the voltage, you can get the what you can say the temperature. So this is here. These are very rapid, and you can see the time constants are like in the order of milliseconds. And this is a very special type of one, optical pyrometer. I think most of you might have studied, know about it. So this is also called as a disappearing flame pyrometer. It generally used for measuring the high temperature object like the furnace or the melting furnace and all these things. And so here you can see here the radiation emitted from the target is of course focused through the optical lens. So lens, and this optical lens helps the radiation to fall on a red filter. Basically, the red filter allows the radiation only in the range of about 0.6 to 0.65 micrometer. So this wavelength only, in this wavelength range only, our human eye will be more, of course, sensitive. And so what we can do, so here there is a filament, and you see here which is placed in between the objective lens and the this red filter. So you can control the current flowing through this filament so that brightness can be varied. So you have to keep controlling the current in such a way that the brightness of the flame disappears. So at this point, the brightness of the filament will be equal to the brightness of the target. So by manipulating the unknown temperature body and the current flow, then manipulation means by calibration. By calibrating the unknown temperature body with the current flow in the lamp, so you can measure the temperature. So the applications are, it's mostly used in the temperature measurement of furnace, and where the human axis cannot be, of course, the parameter. In such situation, we can use it. It's mostly meant for high temperature application. If you want to measure the temperature in the range of about say 1500 to about 3000 or 4000 degrees Celsius, you can use this one. So now the IR thermometer, I think most of you familiar about this one. Now this the IR thermometer is used everywhere, for detecting our body temperature. So basically, this thermometer works in the IR range. They between say 0.7, maybe 0.8 micrometer up to about 20 micrometer. This is the range. So basically, the radiation received in the IR, the infrared ray, that will be concentrated to a photon detector. The photon detector produces the electricity. Then the electricity will be correlated with the temperature, and there will be a temperature display. You can see it. Again, these are very, very rapid, and maybe when you focus on your body, and you can get. So here, the one important thing is the focal, the focusing distance. For the medical application, the focusing distance should be about 1 meter to 1.5 meter. So again, the focusing distance, that is the distance at which the distance between the target and the instruments, it will varies from the focal area. Basically, the focal area, or maybe the distance, maybe in the other words, the focal area divided by the distance. So this, of course, it's an important parameter. Each instrument will be designed, for a certain focal length. So you have to use the instruments within that focal length. So if you go or maybe nearer to the target, or if you go away from the target, then you will have the problem. Again, these instruments are designed for a particular emissivity. So for the medical use, our human body will have the emissivity in the range of about 0.65 to 0.7. With that range only it is designed. So the IR camera, thermometer, which is designed for medical use, cannot be used for other applications. So that, of course, you have to ensure. So for the larger version, industrial version, and where you have the option for entering the emissivity value. Okay, so before using the temperature sensor, one should know about the errors in temperature measurements. So you should not think that you should not like take whatever the reading you got from the instruments are granted. You should not take it as a granted, but there could be a lot of errors. This error can be, for example, if you use a thermocouple, there will be a lead wire conduction. That also you need to take it. Suppose now I'll give you an example. I am asking you to measure the atmospheric temperature by using a simple class in Mercury thermometer. There are two cases. One, I am asking you to stand under the tree, and in another case, I am asking you to stand in the visible sun. But in both the cases, you will be measuring the the same temperature of the atmosphere. You will not, in both the cases, you will not get the same temperature. If you stand under the tree, your thermometer may not focus the sun. If you stand in the clear sun, then your thermometer may focus your sun. So there will be a the heat exchange between the thermometer and the sun, so which leads to the error. So all these things, of course, you must consider. And particularly when you use the thermocouple, you make sure that there should not be any lead wire, there would not be any conduction loss. Particularly when you use the thermocouple, when the thermocouple focus the cold wall, and then there will be a radiation error. So in that case, we need to go for there is so-called the radiation shield. That is very, very important. So all this basic idea you must have when you are going for a temperature measurement. Anyway, this is a very big topic. Anyway, I cannot cover all these things. This is a very simple example. Suppose here there is a thermometer which is facing a visible body of having different temperature. So according to the gauge balance you will have. So here the TT is the temperature measured by the sensor. Definitely it will not exactly sense the value of TG. It will be different value. So that of course you must of course consider. So now we will move to the second one, that is the pressure measurement. Okay, pressure is of course it's a very important thing which is also associated in our day-to-day life. So the absolute pressure, gauge pressure, and vacuum pressure. I think most of you familiar about the definition. So the vacuum pressure is we refer the vacuum pressure below the atmospheric pressure. Absolute pressure is nothing but here the absolute pressure is measured with reference to the vacuum pressure as a reference. And gauge pressure is nothing but it's a pressure measured above the atmospheric pressure. That is the gauge pressure. So in case of the liquid, and we have three types of pressure. One is a static pressure, stagnation pressure, and dynamic pressure. Static pressure, actually, it is measured when the fluid is at rest. Stagnation pressure, it's measured when the fluid is brought to rest isentropically. This is very, very important. It's a stagnation pressure. Dynamic pressure, which is related to the the velocity of the fluid. So these are the units commonly used for pressure measurement. That of course you can see it. And there are of course several methods generally used for pressure measurement. We have the gravitational type and dead weight type, liquid column, then the elastic pressure transducer, and force measurement devices. By using load cell, you can measure the pressure. Electromechanical sensor, electrical sensor, then thermal sensor, and ion sensor. The last two options are meant for vacuum pressure measurement. Just I quickly go through it. So basically, it's a dead weight pressure tester. It's basically it's not a pressure measurement instrument. Basically, it's a pressure calibration instrument. Okay, here you can see here there is a platform over which the known weight will be, of course, standard weight will be applied over it, and the other limb here the unknown pressure transducer. The pressure transducer which need to be calibrated can be connected here. So, for example, on the platform, just you apply 1 kg of weight, which will produce 1 bar pressure, or which will produce 1 bar pressure to the the pressure transducer, and with the known input you can see what is the output of the pressure transducer. In that way you can calibrate the pressure calibrate the pressure sensor. Here you can see here there is a curve. Basically most of the pressure sensor gives the output in the form of milliamps. So for example when no pressure is applied, the default value is 4 milliamps. Then when you apply, in this case, the pressure transducer range is 0 to 200 bar. So at maximum scale, you will get the 20 milliamps. So this is the instrument's output. So you can make a plot between the milliamps and the applied pressure. So with that, you can get the equation. So from this equation, you can get the, of course, the pressure output value. So this equation can be of course, entered into the data system. So that whatever the pressure transducer output that will be directly converted into pressure. Okay, So another one is manometer. Basically, these all are the gravitational type of here the pressure is the unknown pressure is balanced by the weight of the fluid column. Okay, so you see here this is a U type. Basically, the simple U type one. So in the U tube, the manometric fluid will be taken. It can be water or it can be mercury. Depends on the pressure range. You can choose any of the manometric fluid. So basically one limb of this U-tube is connected with the unknown pressure. Other one will be exposed to the atmosphere, so that the pressure measured from this manometer will be the gauge pressure. So by using this simple equation, you can get the the value. So this is the most common kind of common configuration. So here you can use two fluids. One can be water, and suppose if you want to measure the the pressure difference between the two streams, then this kind of scheme can be used, and one can be water, another can be air, or maybe another oil, and then the manometric liquid can be the mercury. So you see here it's a simple force balance between the two limbs. By using this force balance, you can measure the unknown pressure in terms of head. Okay, there are different several versions like the well type. Suppose the applied pressure is very small, then the displacement in the U-tube manometer will be very small. So in that case, you can go for the well type manometer. Well type manometer, it will enhance the displacement, and still if the applied pressure is very small, then you can go for the inclined manometer. So here the displacement will be magnified by a factor of 2 or 3. Okay, these kind of versions are available. So this information you can get it from this one. So here what I want to tell you, suppose if you choose the mercury, the pressure range is, say, if you want to measure the pressure delta P above say 500 maybe above say 500 kilopascal or maybe 100 kilopascal, you can go for mercury. So if the pressure delta P is less than 100 kilopascal, you can go for water, or if it is say less than say 50 kilopascal or maybe in the range of pascal, then you can go for the inclined type manometer. So the here selection of manometric fluid is purely depends on your operating range. You see what is your operating range, accordingly you select the manometric fluid. Okay, right? You should not go blindly with the this one. Suppose we want to measure the pressure difference of the range of pascal. If you choose the mercury as a manometric fluid, you will not get any displacement, because the density of mercury is the 13,600 rho GH. Then if you see, let us take the pi kilopascal equal to rho GH, then you find out the value of H. That may be in the in the range of micron. So how do you measure the micron in practical this way? It's very difficult. Okay, so that of course you have to think about it. So next one is the Bourdon tube. Basically it's a very simple and reliable. I mean, you can say the the instrument, which is having a elastic tube of non-circular cross section, and the one end is connected to the pressure inlet, and the other end is connected to a needle through the suitable spring or gear mechanism. When you apply the pressure, the non-circular cross section try to become circular in shape. So therefore, there will be a bending moment. There will be a bending, and this bending will be transmitted through the pointer through a suitable the spring or the gear mechanism. So with that you can measure the pressure directly. It's a direct display, and I mean this by using a Bourdon tube you can measure the pressure in the range of about from atmospheric pressure up to maybe about 1,000, or maybe you can also go for few thousand bar. And there are several versions, like for example, this kind of spiral one can be used for small range. The C type can be used in the range of say 100 bars. This kind of a helical spring it can be used for above 100 bar pressure. Okay, so this I will leave it. Now coming to the moving fluid, as I already mentioned, in case of the moving fluid, we have the 3 type of pressure. Static pressure, this can be experienced and measured when the fluid is at rest. Dynamic pressure, which is close to the which is referred to the dynamic energy or the velocity of this one. Total is the stagnation pressure. So now you see the simple the schematic. There are 2 points, 1 and 2. One is in the free stream where the fluid is moving, and 2 is it is on the object, or maybe some kind of obstruction where the fluid is brought to rest isentropically. So if you apply the Bernoulli's equation between these 2 points, since both the points are in the same datum, so therefore the datum energy will be neglected. So the first one, the P1, plus the rho into V1 square by 2 equal to P2 and rho V2. This is the one. The V2 is 0 because it's the stagnation point. So then the P2 becomes the stagnation pressure. That is your total pressure, which is equal to P1 plus rho into V1 square. So by measuring in this way, you can measure the this pressure, total pressure. So we have anyway, I will go for it. Here this is a pitted tube. It's a very simple instrument. In the pitted tube, it's meant for measuring the stagnation pressure or the total pressure. You see here there is a capillary. You see here the capillary. This capillary opening is kept in the just opposite to the flow direction, so that the flow will be directly impinge into the capillary. So the capillary is connected to a manometer. You see here. So the pressure, total pressure of the or the stagnation pressure of the fluid experienced by the fluid will be communicated to the manometer. By measuring the fluid displacement in the manometer, you can measure the total pressure. This is the stagnation pressure. It's a pitted tube. Another is a static prop. Here the opening, the whole opening is made in the circumference of the tube. You see here in the circumference. In the circumference, that means here the the pressure is measured in a perpendicular to the streamline. Okay, so in the perpendicular to the streamline, so it will not, of course, this pressure will not be influenced by the speed of the liquid. So this is your static pressure. Again, the same method. You can make several. Maybe you can usually 4 or 6 holes will be made, and on the circumference, all holes will be connected at the center, which is your capillary tube connected to, and which is further connected to a manometer. So you can measure it. And then for the measurement of dynamic pressure, you combine both the static and the pitted prop. That will give your the dynamic prop. So so you see here the stagnation pressure is measured at the center, and the static pressure is measured at the circumference. The difference between these two will give your dynamic pressure, which is your velocity pressure. Okay. So here there is an issue. Maybe if you see in this figure, suppose this hole, maybe now you come to this one. This static hole, this hole, this is static. This hole is close to the nose. So in that case, the probe will not measure the correct value of static pressure, because in that case the static pressure experienced by the probe will be lesser than some value because of this effect. Now the static hole, this hole is close to the stem. Basically, the stem stagnate the flow. It will stagnate the flow because of the stagnation effect. What will happen? The pressure experienced through the static holes will be higher than the actual value. So there will be error. So that is called as the the stem effect and nose effect. So when you are designing this pitted static prop, and you have to make sure that the stem effect, there should not be any stem effect, and there should not be any static effect. So usually when the pitted static prop is designed, this of course effect will be taken into consideration automatically. You don't need to worry about it. So next one is the potentiometer. In the potentiometer pressure transducer, it's a kind of electrical type one. So here you see here, it's very simple. The arm of the potentiometer is attached to a pressure bellow. Okay. Now, when you apply the unknown pressure to the pressure bellow, what happens? The pressure bellow will expand. Because of the expansion, the wiper ram that will move across the Wheatstone bridge, and there will be a change in, of course, because of the change in resistance in the Wheatstone bridge circuit, then you will have a voltage. By measuring the voltage, you can, of course, measure the pressure. This is a very simple techniques, and it can be used anywhere between, say, from atmospheric pressure up to maybe about several hundred bar pressure. Then the capacitance type pressure transducer. This is a very special type of transducer. Basically, here there is a thin metallic diaphragm and of known capacitance. When this diaphragm is exposed to unknown pressure, because of the you can say the external pressure, its capacitance will change. By measuring the change in capacitance, then you can measure the unknown pressure. So you see here in this figure, there are two openings. One opening you can it can be a reference pressure, or maybe atmospheric pressure, or maybe pressure of another stream. And in another opening you can give the what you can here you can provide the the pressure of a unknown stream. So based on the requirement, this capacitance type transducer can be absolute transducer. It can provide the absolute pressure, or can provide the gauge pressure, or it can provide the differential pressure. So this is the only instruments if you want to measure the the difference between the two pressure stream, which is varying with time. Okay, so in that case, this is the only instruments you can use it. For example, now you have two gas streams, and in both the gas streams, the pressures are not constant; they are varying with respect to time. So if you want to measure the delta P in real time, and so this is the only instruments which can, of course, adapt such kind of variation. Okay, electromagnetic sensor, again, this is similar to the potentiometer. There is a pressure bellow, and the pressure bellow is attached with the conductor. The conductor is kept in between the two electromagnetic, electromagnets, or maybe a permanent magnet. So if you apply the pressure to the pressure bellow, what happens? The conductors will move between the electromagnet, and which will induce the EMF. By measuring the EMF, you can measure the pressure. Again, this instrument is meant for measuring the dynamic pressure, not the static pressure. Even static pressure also you can do it, but it is more suitable for the dynamic pressure. Application, of course, any normal application you can use it. It can be used of course, from atmospheric pressure, you can go up to about several thousand, of course, bar. The next one is piezo-resistive type sensor. This is a very, very special type of sensor. In this sensor, there is a piezo-resistive type crystal. So the special property of this the crystal is when you apply any external force over this crystal, it will induce the EMF. The induced EMF from the crystal will be directly proportional to the the external force. So by making a correlation between the induced EMF and the external force, the pressure can be measured. The one special characteristics of the sensor is the EMF produced from the sensor will decay immediately within fraction of a second. The EMF will disappear. So therefore, this sensor is mainly meant for measuring the transient pressure. It cannot measure the if you are using it for static pressure, of course you will end up with having wrong value. Okay, that of course again this is very good sensor and cost effective. It can be used up to about 1000 bar. It will give very rapid response. Here the response time may be less than about so a few hundred microseconds. Very good and excellent. But only thing is this sensor need to be calibrated for in once in 3 months or once in 6 months. If you are not calibrating the sensor periodically, then you will end up with having wrong results. So you don't think that once you purchase the sensor, fit into the experimental setup, and it will give the value. It's not. So for every 6 months, you need to calibrate the sensor, because these crystals, once when it is subjected to the repeated strain, and there will be a drift, so which need to be, of course, measured periodically. You can see here, this is a photograph of view of this sensor. Okay, so now let us move to the low pressure measurement, McLeod gauge. I think most of you heard about it. McLeod gauge is the standard for vacuum pressure measurement. The units of vacuum pressure is it's a tar. 1 tar is equal to 1 mm of Hg. Okay, so basically the McLeod gauge works based on the principle of Boyle's law, and we'll see here. Basically, in this McLeod gauge, so there is a calibrated volume. It's a bulb. Whose volume is precisely calibrated. On the top of the here the calibrated volume, you can see here there is a capillary. This capillary, in the capillary there will be a calibrated scale will be attached on the capillary. So what you can do, so in this McLeod gauge, the principle is that the unknown pressure is the unknown low pressure is compressed to a level which can be measured by a simple manometer. So we need to compress the unknown low pressure, gas pressure to a level, to a value at which a simple manometer can be measured. So by this is the principle. So what you can do, first you admit the whole gas till this point, then you press the plunger till this at this point, and there is a mark here. So at this mark, your PI will be equal to the pressure, unknown pressure will be unknown pressure of the gas will be equal to the pressure which is maintained in the so-called in the bulb volume. So the the bulb volume of the bulb, and so the volume of the bulb V into PI will be equal to. So now after that you pressurize it, you reach the scale. Once you reach the scale, then you can get, this is the value of H. From the value of H, you can get the value of pressure. Then the volume of this capillary can be measured. So therefore, your the volume of the bulb multiplied by PI will be equal to your P2, which can be measured by from the manometer, and the H, that is the volume. So that is your this one. So in this equation, all the quantities are known except the PI value. So by using a simple P1 P1 into V1 equal to P2 into V2, simple relationship, you can get it, but provided here the temperature need to be constant. Okay. So now we'll move to the Prani gauge. The Prani gauge, these are meant for the low temperature, low pressure measurement, vacuum pressure. So basically, when the pressure below say 1 - 1 torr, the thermal conductivity, the thermal conductivity of the gas will be directly proportional to the pressure. Okay, higher the pressure means higher the thermal conductivity. In case higher the thermal conductivity means higher the heat transfer. Yeah.
The low temperature pressure skip because now it's 6:34.
Okay. Okay.
You can throw some key important flow.
Okay, fine. So I will skip it. Okay, so maybe this I will explain. Maybe already 6:40. Okay, so I can take up to 720, 750, no problem. So coming to the high pressure measurement, actually here basically these are the metallic strips. When the metallic strip is subjected to pressure, then its resistance will change by observing the change in resistance. One can get the pressure. So with this sensor, one can go up to 1 lakh bar pressure. Okay, so I will skip it now. Coming to the flow measurements, the flow measurement is a very important in our day-to-day life. So you see here in the petrol bunk and milk distribution and water metering system. Here the quantum of measurement is huge. Even if you take a petrol pump, even if there is a accuracy of maybe about, even if there is error of say 0.01%, you see the amount of liquid to handle. So even if you take 0.1% of error in a day, if you see this one, then it will be very huge. So therefore, particularly in the flow measurement, we have planned so many techniques. Even there is a separate subject on flow measurement itself is a separate subject, and we teach in the undergraduate level. There are so many techniques are available. Maybe this is the summary of the techniques. Just I will try to highlight some of the techniques which commonly used in our R&D field. So the pyrolysis mass spectrometer, which is well advanced, I can say the versatile and more reliable, the technique can be used for any flowing media. And differential pressure one, these are the faults, and these are the simple Venturi, pitted and orifice meter. And then we have the rotometer, and basically it's by balancing the weight of the float with respect to pressure force on the buoyancy force, it can measure. Then we have the target type flow meters and positive displacement flow meter, thermal mass flow meter, turbine type mass flow meter. There are so many. I don't know how much I can cover. Maybe we'll see quickly. We'll see. So we have seen by using a pitted static prop, one can get the velocity. Once you know the velocity, then you can get the flow rate multiplied by the area of cross section. So pi d square by 4 into V will give you the meter cube per second. This is a very simple thing. And you can see here, this is the how it can measure by using this kind of manometer. You can measure the value of H. With the value of H, you can measure the flow rate. But the only thing is, this kind of a spherical, we have to go for, when you go for the pitted static prop, you have to go for this kind of a spherical gate. Basically, the spherical gate will give the, the flexibility in aligning your tip within plus or minus 38 degrees. Basically, these props need to be aligned perpendicular to in parallel to the streamline. If there is a inclination, you will end up having the error. So if you choose the spherical head, so it can accommodate some inclination. These are the different versions of this one. So it can be used, from low flow range to high flow range. It's very simple, and you can very easily insert into the flow medium, and you can get the flow rate. Okay, so now coming to the differential pressure flow meter, here the flow is measured by measuring the difference in pressure between the two locations. What you can do, you allow the flow to go through in a change in cross section. When the flow flows in a flow through a change in cross section, there will be a pressure change. By measuring the pressure change, then you can measure the flow by applying the simple Bernoulli's equation. So the equation is very simple to see here. You see here, there is section 1 and 2. There is a change in cross section. So when the flow takes place from 1 to 2, because of the change in cross section, its velocity will change. By measuring the velocity will change. Then and also pressure will change. By measuring the pressure drop between these two sections, then the velocity can be measured. Then by applying the continuity law, this one, the simple the law of continuity. This one, you can measure the flow rate. So these are the simple expression in most of you this one. But what is interesting is Just I will show the interesting things. Now you see here, there are three type of configuration here: Venturi, nozzle, and orifice. In case of the Venturi, whatever the pressure, basically the Venturi, you see, you slowly, suddenly you converge the flow and slowly then diverge the flow. So by doing this, so whatever the pressure loss happened while converging the flow, that can be recovered by slowly diverging the flow. So here you can recover almost like 99% of the pressure loss. Therefore, here the coefficient of discharge can be anywhere between 0.95 to it can go up to 0.98. In case of the the nozzle, basically in case of the orifice basically it's a kind of a thin metallic sheet. We have to insert in the flow. There will be opening. So in the orifice, you cannot recover the pressure loss. So the coefficient of discharge, maximum value of coefficient of discharge from the orifice flow meter is maximum about 0.5 to maybe 0.6, not more than that. So therefore, when you go for the orifice, you need to precisely estimate the coefficient of discharge. Without that, you cannot use it. So I think all this expression will be known to you. And so now you see here. So basically, whenever you use this, meter, and the coefficient of discharge is the function of velocity. Okay, so basically now that means the flow meter, the Venturi or orifice and nozzle flow meter, this flow meter need to be designed for a particular flow rate. That means the flow meter which is designed for one particular flow range cannot be used for other flow range. If you are using for the other flow range, you must estimate the value of coefficient of discharge. Then that means you cannot use the same value of coefficient of discharge for a wider range. If you use it, then you will end up with having the error. So whoever is using this kind of flow meter, you must know the knowledge of coefficient of discharge, how it varies with respect to velocity. Okay, another this is basically it's a Venturi meter. As I already told you, the converging angle will be maybe about 10 to 15 degree, and diverging angle will be 4 to 6 degree. Suddenly you converge and slowly you diverge. So that you can recover all the pressure loss. So and then again there will be pressure tapping. I think which I have not shown it here. So whenever you make particularly when you use the the nozzle. This is the nozzle. This is the orifice. So you have to make a tapping. One tapping is in the upstream side. You can make a tapping maybe 1 inch from the this nozzle, and the downstream side it should be ½ inch. You have to the ratio should be 1 to 1.5 inch. Basically, the downstream side, the vena contracta will develop exactly ½ inch from the this one. So that means the tapping should be taken at the normal pipe, and another tapping should be at the close to the vena contracta. So between these two sections only will have the maximum pressure drop. So whenever you make the pressure tapping, this of course you must remember about it. Okay, so okay, fine. The elbow type flow meter also it's used in the refinery industry. So basically, when the flow is circulated to a elbow because of the centrifugal force, then maximum pressure experience at the outer side than its inner periphery. So we need to take a pressure tapping between the inner side bend and the outer bend. So between these two sections will give the pressure drop. From the pressure drop, you can get the the flow rate. So then the rotameter, this is a very special type of instrument, and it's very cheap also. Most of the people use it. But of course, many times what will happen, people of course end up with using this instruments, without having background. So it's when you are using the rotameter, you need to be very careful. Basically, in the rotameter, the weight of the float, this is balanced. The weight of the float, basically it's the downward force, which is balanced by the combination of the buoyancy force acting on the float and the track force. Okay, so here the rotameter is, you see here the flow area is tapped to have the force balance at any location. But at any given flow rate, the float itself find its in a positions with respect to the flow rate. For a given position, the net upward force acting on the float will be equal to the net downward force. So here the rotameter designed for, or the float designed for one particular liquid. The float will be designed for one particular liquid. Suppose the float which is designed for air cannot be used for maybe water, maybe some other application. You cannot use it. And similarly, there is one important thing here: the ratio of the density of the float to the density of the flowing liquid. This should be 2. For having the better accuracy, the ratio of density of the fluid and the flowing liquid. This should be 2. So if it is more than 2, then you will end up with having the accuracy. Again, the rotameter is designed for, as I already mentioned, it is designed for one particular density. The flow meter, the rotameter can take care of the density variation, maybe about maximum about 2 to 5%, not more than that. The density variation is more than 5%, then the rotameter cannot give the reading. So the rotameter is ideally suited for liquid flow measurements. You cannot, of course, there are versions available for air, but if you use it for air measurement, then you will not get the accurate reading. So this, of course, you must, of course, keep in mind. So in the rotameter, Q is equal to where A is the rotameter constant and AT is the basically it's a what you can say the flow area, which is the function of the displacement, and AF is the area of the flow. So in this expression, K is constant, AF is constant. The only variable is AT, which will vary with respect to flow position. So by observing the flow position, measuring the flow position, then the flow rate can be measured. So in the rotameter, you can see there will be a calibrated scale. So again, the rotameter is designed, it should be kept vertical. This is very, very important. And even if you keep some degree inclined, then you will have a problem. So, and again, it is meant for the steady state flow. It cannot measure, unsteady flow. And again, the rotameter also used for very clear fluids. If there is any contamination in the fluid, and you cannot use it, and it's ideally suited for low density flow like water, and if the viscosity is too high, then of course you cannot use it. This is the photographic view. So the best accuracy is about 2% you will get, provided if you use the rotameter carefully. And the pipe diameter can be anywhere between ½ inch to, you can go up to maybe 10 inch. The versions are available. So then the target type flow method is mainly used for large capacity. One, you can use it for both gas and this one. Here there is a target. You see here there is a kind of a flat, flat kind of a target. This is target. This target is of course connected to a pressure, maybe the kind of a strain gauge sensor. So when the flow takes place, flow will hit the target. So it will produce kind of a strain which is measured by the strain gauge. By measuring the strain, then the track force can be measured. From the track force, the unknown velocity can be measured. So from the velocity, you can get the flow rate. So again, the pipe size can be from ½ inch to, you can go up to maybe about 6-inch diameter. And sensitivity is also reasonable. Accuracy also. Again, accuracy depends on how best you are calibrating the instrument. Okay. The turbine type flow meter is a very, very simple type flow meter. It's a first order type flow meter. Here there will be a turbine, plates which will be kept in the flow bath. When the flow takes place, the turbine will rotate by observing the rotation of the turbine, and you can measure the flow rate. So here again the response is, it's very fast, very simple, and but the only thing is since we need to of course install the turbine inside the pipe, so it will offer the pressure drop. That of course you have to see. And electronically also you can measure. There will be a proximity sensor. The sensor will be kept in the outside the tube. Basically, the sensor will sense the number of rotation of the turbine. So from the number of rotation of the turbine, so you can get the flow rate. So this can be used for both and unsteady, this one, and for both and liquid and gas, the flow meters are available. Okay, so as I already mentioned, this can be used anywhere between 0.1, maybe 0.5 inch diameter up to about large size, like you can go up to 10 inch or 20 inch diameter. These are also available. And if the diameter is more than too big, and we have to go for the ultrasonic type flow meter. And basically it's a non-contact type flow meter. Of course, because of the time constraint, I am not covering it, but it's a special type of flow meter available. And suppose if the fluid is highly hazardous and which you cannot touch, so we can go for the magnetic type of flow meter. But in the kind of magnetic type flow meter, the fluid should have some minimum conductivity, then only you can use it. So this is very simple. And see here, the pipe, basically the pipeline is enclosed with a permanent magnet, or it may be electromagnet. When the flow takes place, because of the movement of the fluid within the magnetic field, and so the EMF will be induced. By measuring the induced EMF, you can measure the flow. So basically Q is equal to the U, that is U bar, which is the velocity, and B is basically it's a magnetic flux, and L is the diameter of the tube. So here B is the L is constant, and the velocity B also, it will be a kind of this constant again. So the E will be directly proportional to your, power will be direct, electrical power will be directly proportional to velocity. So therefore Q is equal to K into K is nothing but the meter constant, which is the function of the tube diameter and then the magnetic flux, and E is your electrical output. So by making the relationship between the electrical output and the the discharge, here the discharge can be, of course, the measured. Very simple, and it's here, of course, there is no flow obstruction, technically no pressure drop, and it can measure flow in both the direction. It can measure both in steady and transient flow, and this is insensitive to viscosity and density change and etc. So it can be used for any hazardous fluid also. These are the advantage. And the positive displacement meters, I think this already you might have seen it in the many things. So anyway, this I will skip it. It is not so important. I think many of you have seen it. Just I will show you this K type flow meter. The flow will be, forced through a case in where two gears will be there. Because of the velocity of movement of the fluid, the gear will rotate. By observing the rotation of the gear, you can measure the flow meter. So each rotation, it will disperse some fixed amount of the fluid. Like we have the vane type flow meter. That means each rotation of the vane, it will disperse some fixed amount of the fluid, like the lobe type flow meter. Actually, all these type of flow meters are meant for measuring high viscous liquid or water and all these things. It can be used. These are the one. And now this is very, very special one, pyrolysis type flow meter. Suppose the fluid is having the mixture of both the gas and liquid, and its density is also varying, its pressure is also varying, and its temperature also varying. Then in that case, none of the techniques which I have discussed will not suit. So the only suitable technique is the pyrolysis flow meter. Here, the oscillation of the fluid is measured in terms of the frequency shift. By measuring the oscillation of the fluid, you can measure the mass directly. Okay. So basically, in the pyrolysis mass meter consists of a U tube, and which is set to vibrate at constant frequency. It will vibrate like this. Okay. Set to vibrate at constant frequency, and in both the upper side and lower side of this U tube, there will be a sensor. Basically, the sensor will sense the oscillation frequency. Now, if we supply any fluid through this U-tip, which is oscillating at a frequency, then because of this entry of the fluid, then the tube will twist. It will twist like this. Okay, it will twist like this. By measuring the time lag between this, the twisting, then you can measure the, the mass. So basically, this was invented by the French engineer. His name is Pyrolysis. So because of his invention, this meter is named after his name. So this is very very reliable one, and very highly accuracy. Here the accuracy will be 0.01%, and it can be used anywhere between 0.25 quarter inch up to from quarter inch to about 8 inch. It can measure any flowing liquid. It can be liquid or gas, or the mixture of liquid and solid, or mixture of liquid and gas, whatever may be the one, it can measure. And in addition to that, here the interesting feature of this instrument is it can directly measure the mass. Okay, which can be transient. Even it doesn't care about the change in pressure, change in density, or anything. Okay, so it's a very good instrument, and it is more. You can use these instruments mostly for the gas, high pressure gas, particularly if you want to measure the hydrogen, because the hydrogen density is very, very low. Okay, you cannot use the normal flow meter. So therefore, this is the best one. Or if you want to measure the helium, you can use it. Or if you want to use the water, you can use it. Okay. So the thermal mass flow, basically this mass flow works based on the heat transfer principle. It's a very simple. There will be an electrical coil, heated electrical coil, and then the fluid will be supplied through this coil. And then since the wire is heated, there will be heat transfer from the wire to the fluid. By measuring the heat loss, from the wire, or the heat transfer from the wire, you can measure the flow rate. Basically, the Q is equal to the amount of power supplied to the heater will be equal to MCP delta T, where M is the mass flow rate of the fluid and CP is specific heat. Delta T is the temperature difference between the inlet and outlet of the meter. So basically, the wire will be maintained at a constant temperature. So therefore, by measuring the power required to maintain the temperature of the wire at constant temperature will be equal to the total heat transfer. Okay. So with that, you can measure this one. Of course, there are versions. Either you can you can maintain the temperature of the wire as constant, or you can supply the constant power to the wire. In both the cases, you can do it. So the best example is hot wire anemometer. So it's a very simple one, but again the thing is for each liquid this need to be calibrated. Okay. Calibration is very, very important. So whenever you use this such kind of flow meter, first you need to calibrate with respect to standard output, then only you can use it. Okay. So maybe another I may take another maybe 5 minutes, 5 to 10 minutes. Now the third one, so the uncertainty, this is very, very important, because as I already mentioned that, so of course you should not take it granted, the granted of this instrument's output. So for example, if you want to measure, if you are going to measure the heat transfer rate, let us take MCP delta T. Here the mass flow rate need to be measured, and temperature difference also need to be measured. Or if you are finding the efficiency of a engine or any measurement, there will be 2-3 measurements. Each measurements will have its own error. Okay, so when you are based on maybe 2-3 measurements, if you are estimating some value, then your value, estimated value, will have more, of course, uncertainty. So that, of course, you need to estimate. So therefore, any, of course, the measured quantity should be associated with the error. So then only it is meaningful. So for in reality, when you are doing the experimental analysis, you must do the error analysis. That is very, very important. So whenever you are writing a journal paper, or maybe writing a technical report, your experimental data should be, of course, associated with the error bar. The error bar is very, very important. If you are not, of course, providing the error bar, then your result, there is no reliability on your results. Okay. So we will see how it can be done. So basically, the true value, actual value, will be equal to the measured value plus the error. This error can be of systematic error. The systematic error is, due to the improper calibration, or the inherent feature of course, the instruments, which can be determined by using a calibration. Whereas the random error, is mainly due to the random means it's you cannot predict the source. It can be anything. So maybe due to improper usage, or due to the environmental influence, or due to the influence of the electromagnetic effect, and etc. These sources cannot be traced. Since the error is part of random error, which is random in nature, uncertainty in nature, therefore error is called as uncertainty. Okay. So now we will see how we can, of course, estimate the uncertainty. Let us assume n, that is the value which you are going to estimate, which is your dependent parameter, which depends on several independent parameters. Those independent parameters are like U1, U2, U3, U4, etc. Basically, n is the function of the several independent parameters. So independent parameter, that is that parameter you can vary independently without affecting the other parameter. That's why it's called as independent parameter. So in each independent parameter, there will be error. So those errors are like delta U1, delta U2, delta U3. These are the error involved in each independent parameter. So therefore, now the total uncertainty, that is the total uncertainty involved in the estimation of your dependent parameter, that is a delta n, will be equal to the function of U1 plus delta U1, comma U2 plus delta 2, and etc. So now you expand this expression by using a simple Taylor series, then you'll be getting like this. Then if you simplify, then your delta n, which is nothing but the total uncertainty involved in the estimation of your dependent parameter, will be equal to the dou f by dou u1 into delta u1 plus dou f into dou u2 into delta u2, and so on, where dou f is the full function. Okay. So now you need to basically, the function need to be partially differentiated with respect to individual this independent parameter, and then this differentiate quantity should be multiplied with the uncertainty or the error of individual measurement. Then you sum it up. So this will give the total uncertainty. Sometimes what will happen, maybe in this equation, this value may be negative and this value may be positive, and they may be equal of magnitude. If you sum two equal magnitude of having different sign, then they will cancel out each other. So therefore, you need to take the RMS value. So you square the individual values, and finally you take out of the root. So this will give the total uncertainty. So I am giving a simple example. So basically, this is the head loss in a simple pipe flow, which is related to friction factor, length of the pipe, B is equal to V square, and 2, and G is the constant, and D is the diameter. Here the measured quantity is diameter. Of course, you have to measure. Length of the pipe, yes, you have to measure. Velocity, you have to measure, and friction factor, you have to measure. So the friction factor depends on the 4 measured quantity like F, L, P, and D. Okay, these are the 4 measured quantities. So the uncertainty error involved in the individual quantities are given here, like 2%, 4%, 1%, etc. Since G is the universal constant, that you can ignore the error in the G. So here is the expression. So delta H is equal to, so these are the values, and each then you have to differentiate the H with respect to individual independent variable, then you will get this value. Then you substitute all this value in the expression, then you put the respective value, and you will be getting the final value. So the final value will be, so in all these quantities, H will be common, that you can take out, then you bring the H the other side, then it will become delta H by H. Basically, this is the in terms of, this will be in terms of percentage. Okay, so the value will be plus or minus 0.03. So that should be expressed in terms of percentage. If you multiply by 100, so the total error involved in the estimation of the head loss will be 3%. So this should be, so whenever you are taking this value, see, for example, in this value, see the L, so the TH by TL, whenever you are the delta L. Okay, so here you have to take the, this is called inaccuracy in the length measurement. This is the inaccuracy in the velocity measurement. This is inaccuracy in the diameter. So whatever the value you are taking here, L and V, these values, maybe for example here. Yeah. So now comes here. This is delta TL by L. So here the L should be the maximum value you have to take. You should not take the minimum value. See, some people, just to show their, bring it to the uncertainty to a lower level, they take the smaller value. You should not take. So whenever you take the, whenever you are estimating this quantity, the quantity should be estimated based on the maximum value. You must show the maximum uncertainty, okay, not the minimum uncertainty. That means every data point, this uncertainty will vary. Okay, that means each data point you must estimate the uncertainty. Maybe in Excel you can do it. This you have to do it. So now when you are doing the general, of course, data analysis, of course, when you are doing each, of course, experimental run should be, at least it should be conducted for minimum 3 times, and you have to ensure that each, all these 3 readings should be, of course, consistent. If there is an inconsistency, then again you have to do the experiment. So when you are doing the experiment and there will be some kind of irrelevant, inconsistent data, that of course you have to, you have to remove. Then after getting the, reliable the data, then you have to do the experimental uncertainty, which I have explained, and then the results should be expressed along with the experimental uncertainty. And of course, then you have to do all the correlation and etc. So now this is the final one. So the design of the experiment, how you can design the experiment. So of course there are several steps. So before conducting the experiment, of course you need to follow some protocol and some, of course, steps. The steps are, first you need to identify the number of independent parameters. Okay, that is the parameter which affect your the experimental or the dependent parameter value. You need to identify number of independent parameter, and which can be, of course, varied independently without affecting the other parameter. Then you need to identify the number of dependent parameter. Then you need to, of course, do some kind of a simple thermodynamic analysis to study the effect of each independent parameter on the dependent parameter. So this you need to have some kind of a simple thermodynamic analysis. Then based on the simple thermodynamic analysis, so you can find out the most, of course, the influential independent parameter. Okay, so you have to choose only those independent parameter, whereas the least influenced independent parameter can be, of course, clubbed together, maybe in terms of some non-dimensional parameters. You can take it separately. So then based on this one, then you need to optimize the number of independent parameter which you are going to vary in your experimental things. Then each independent parameter, you need to identify the range. Okay, you cannot identify randomly. For that also, you need to do some thermodynamic analysis. From the thermodynamic analysis, you can find out the minimum value and the maximum value at which the independent parameter can be varied. So once you find out the range of each independent parameter, there is a parameter optimization. Of course, there are several optimization techniques are available now, the Duckshing method and genetic algorithm. There are several tools are available, and you can use any one of this genetic algorithm tool or any one of the optimization techniques. You can identify the number of levels to be tested in each independent parameter. Okay. So then after that, then coming to the the selection of instrument part. So for from this value you can fix from all the analysis. You can come to know the range of each measurement, accuracy level required, and the resolution of each the requirement. Based on this, you have to select your instruments. So how your instruments can be selected? Instrument selection should be based on the range, operating range. If it is a temperature, what temperature range you are going for. Then what is the level of accuracy you want? Whether you want plus or minus 1 degree Celsius or plus or minus 2 degrees Celsius, what is your accuracy? And what is your resolution? That is also you need to know. And the response time, whether you need to have a fast response or slow response or the dead slow response. So based on that, you need to find out. And also you need to find out the data transfer option, whether you need to have a digital display or whether you need to have an analog display, what kind of display you want. And then obviously at the end, you need to see the cost and availability of the instrument. So based on all these factors, you have to select the instrument. Once you have done the instrument selection, then you have to do the experimental uncertainty analysis. Then you have to do the selection. So this is the, of course, the way how you can design the experiment. So before, of course, doing the experiments, you need to have a lot of plan, and you need to plan in a very systematic way. And if you follow proper sequence, I am sure that, of course, you will be getting the data which is more reliable and which is more, of course, you can say the value one. So that, of course, you need to do it. So with this one, of course, I thank everyone for your patient hearing. It's almost like 1 hour, more than 1 hour, 45 minutes. Thanks a lot for your attention. So I'm here to take a few questions if you have any query. Now the topic is for discussion.
Thank you, Muthukumar. Excellent coverage. I think I really feared how you are going to cover such a wide area, because starting itself there are 100+ slides. But like a marathon race, you are in a marathon race like a 100-meter race. So that is a thing. I think you must be totally exhausted, because without even a small pass, you are. Dear participants, we can take up 4 or 5 questions, but not through online. I mean, direct.
And they can take, so maybe 1 or 2 questions. I can take it.
Yeah, that's what I'm coming. You can type in the chat box so that because the connecting time can be minimized. So please kindly avoid this thank you messages. That after the session, I will leave for 3-4 minutes time to close the session. Then you can type thank you messages. Now you type only the doubts. Okay. Muthukumar, in the meantime, people type a thing.
Yeah.
My questions are, see, you said beautifully covered so many things. For anything, there is 2 things. One is instruments are available in the market, and another one is we have to fabricate on our own. So it's a very broad question. Of course, very briefly, which one you suggest?
So it's again depends on the application. For example, if you are going for a flow, sensor, for the flow measurement, whether it's a water flow measurement or air flow measurement, if you are confident, you can fabricate your own, the sensor, whether it's a Venturi meter, nozzle type flow meter, or this one orifice. So that you can do it. But when you are making your own instruments, but you need to calibrate. For that, you must have the calibration facilities. If you have the calibration facilities, you can go ahead.
Yeah, fine. If you make ourselves say like orifice meter, something like that, where is the standards available? Because for anything there is you said 1 inch ahead and half an inch.
So these
like
are
that.
available with, of course, there is a national standard. You can find all this standards in the textbook, common textbook. It is available. Even there is a national standard. It is available. It is available in the open literature. In fact, for the orifice, there is a standard. For the Venturi meter, there is a standard. So in case of the Venturi meter, all the dimensions is given in terms of the tube diameter. Similarly, in the orifice also, all the dimensions are given in terms of the tube diameter.
Yeah, but we are not able to find such books in the common market. Probably some specialized libraries.
No, you can find out.
I'm coming.
There is one NIST standards. You can visit NIST website. There you will find out. NIST.
NIST standards.
Yes.
Okay.
Yes. NIST website.
Okay. Fine. I think you can throw some light on data logger, because most of the experiments now data loggers are important. You don't go into the fundamentals, but what kind of data loggers are available in the market? What will be the cost range, and
See, again, the data logger, again, it's based on your purpose. If you are purely going for only temperature measurements, you can get your data logger even at a cost of about 15,000 rupees. It's available. Okay, so basically in the temperature measurements, the output is only voltage. Okay, so that means data logger should have the provision to measure the millivolts. Then after that, there will be option for choosing the thermocouple, choosing the RTD, choosing the thermistor, and then choosing the temperature scale. These are the inbuilt. Okay, so only thing is it's only the out. It's basically this data logger. It takes only the millivolts output. It's very cheap. So those things are even you can get it within about 15,000 rupees. Suppose the data logger which can measure the millivolts, that is you need to use the temperature sensor, you need to use the pressure sensor, you need to use the flow sensor, and you need to use the frequency measurements or resistance measurements. In that case, you need to go for the complete comprehensive data logger. So that is now the Agilent is of course offering which is about 2.5 to maybe about roughly about 2.5 lakhs. But in the instrument, in the data logger, the cost of instrument is very cheap. I mean, the data logger is very cheap, maybe about 1.2 lakhs. But which is expensive is the multiplexer. The multiplexer is very expensive, which will be about 40. Each multiplexer will be about 50,000 to 60,000 rupees. Of course, in each multiplexer, you can have 40 channel, and where 35 channels can be meant for temperature measurements, the remaining 5 channels can be meant for the other measurements. But only thing is, again, the options, how we are going for it, whether if you want to go for millisecond data log scanning or 1 second scanning or 2 second scanning, it's also depends on, the scanning speed. And see, whenever you are using the, data logger, you must ensure that when you are connecting the thermocouple wire should not touch the multiplexer. It should go into the port. Suppose if it is touches externally, then your board will go. And then if it is touches external in the external body, because of the grounding effect, whatever the reading you are getting, it may not be correct. So when you are using the thermocouple, the proper care need to be taken. And one more thing, many people make a mistake. So they make the they connect the thermocouple in the data logger, and the thermocouple other end they'll put it in the water. Okay, they wanted to measure the water temperature. So the thermocouple, when you put the thermocouple in the water, what will happen? Because of the capillary reaction, the water will diffuse into the thermocouple wire. It will go to the data logger. So the data logger will fail. So whenever you are using the data logger, thermocouple for the liquid temperature measurement, you have to be very, very careful. And you should prevent the capillary rise of the water, liquid, through the thermocouple wire. So that many people make this mistake.
Yeah, excellent. There are a few questions in the chat box.
You can read them.
I am asking. You can without much details, you can very briefly. What is the first order and second order instruments?
Okay, so first order basically, it's a very basic fundamental one. The first order instrument is the instrument which is subjected to storage property. Okay, then second order basically it's along with the storage you will have the inertial, the oscillation effect. For you take the thermocouple. Thermocouple basically it's a first order instrument. So as soon as you give the input, the thermocouple will take some time to respond. So there is it's a response time as the time constant. Basically, time constant is nothing but it's a time taken for a first order instrument to reach 63.2% of its initial step input. Okay, so this basically describes this one. Now you take the pressure transducer. In the pressure transducer, you will also, in addition to the storage characteristics, you will also have the oscillating characteristics. So there the so-called the damping ratio will come into the picture. Damping ratio.
Thank you. Next question, Mr. Sunil Jai Krishnan. How to calibrate rotometer based on nanofluid flow for single phase heat transfer experiments?
Okay, so this is very simple. What you can do, of course, I will tell you in a crude way. So you connect the rotometer and maybe set at a particular flow rate. And so what you can do, maybe you can take a simple bucket, maybe bucket of maybe 20 liter, 25 liter. And the bucket volume need to be calibrated, okay? Or maybe in a single mug, later we can measure it. Then you take maybe some seconds, maybe about say, first allow the flow to go through the rotometer, maybe about say 2 minutes. Then see at the end how much fluid is collected. But the only thing is when you're during the flow, you must ensure that the flow rate is constant. Then maybe for 3 minutes, you see how much amount of fluid is collected. You measure it. Maybe by using a simple beaker, you measure it. Then volume divided by the time will give the flow rate. Then you do it at the different, again, you go for the different flow rates. Then whatever the flow rates you are getting, measuring physically, that should match with your, the reading, the display. Okay, so this maybe you can change a different flow rate, set a different flow rate, and physically measure and see and what is showing in the your the flow meter. This is simple way of measuring. And also you can also measure the calibrate the rotameter by using the master flow meter, by either by using pyrolysis mass flow meter or maybe thermal mass flow meter. That is the another way, but this will be expensive. Okay, this is simple way they can do it.
Yeah, okay, so simply time and volume measurement. Thank you, Muthukumar. Another question is, where can we get instruments in the market? How to identify good quality or bad quality?
So
It's a very big question.
It's a very kind of difficult to answer. Where can find means you have to find. Of course, now everything is available in the open source, and you need to, of course, approach the various, of course, the suppliers. And so, before going purchasing your, the instruments, you must know the knowledge of, the instruments. Particularly, as I mentioned, the range, what type of range you want, what is your accuracy level, what is the resolution level, whether you need to have a online recording option or offline recording option. Then all this information you must, of course, you must have it in your hand. Then with that, of course, you can approach the supplier and see whether their instruments or their instruments fulfilling your requirement. Based on that, you can go for it. So my best thing is you approach before buying the instruments. You approach 3-4 suppliers and you talk to them and take their quote. Accordingly, you can go for it. But for the normal information, of course, you can find it on the website. But again, when you go for the pressure transducer and temperature, the transducer and all these things, here the make is coming to the picture, because all make for a same brand, for same instruments. You cannot get the accuracy from all the brands. Some brands are, of course, renowned brands. You will get the better accuracy, reliable accuracy, and some brands may not get the reliable accuracy. So this, of course, you have to get it from your experience. So there is no kind of the standard protocol for it.
Yeah, thank you, Muthukumar. Of course, working in a government organization, he cannot specify any specific brand. That is a restriction he has in any government. You should not specify any brand in any talk. So that is a restriction he has. So going to 2 important questions very quickly, we'll finish. You mean to say quality research depends on quality of testing and the standard of the instruments. Quality of quality testing, quality of instruments. Does it matter for a quality research?
No, not see. Of course, the quality measurement is very, very important. Okay, but even people also with having some fair, minimum instrumentation, they also do the good quality research. So basically, the good quality research depends on your objective. That is what is your objective of your work. If the objective is innovative, and if it is something is new in that, so and even if you use improper instrumentation also, then it will be definitely, it will be published. It's all depends on the nature of the objective, the nature of your problem, the nature of the objective of your research. Okay, so as long as the objective is novel and it is a new, then you'll end up with, of course, good quality research. But obviously, for quality research, need to be supported with the quality measurements.
Yeah, thank you, Muthukumar. Another one important question, sir, actually depends on how much range you measure. If you measure 5K temperature range, then quality of measurement matters. But if you the range is 200 degrees centigrade or 200 Kelvin, then there the accuracy will you can compromise. So, what if it is narrow range, quality of measurement and these things matter. This is another very important question. Is it mandatory to produce NABL based calibration certificate to defend the thesis in the viva-voce examination?
It's not mandatory. For the PhD thesis and even for the your own research publication also, if you calibrate your instruments at your laboratory, and so if you happy with your calibration, it's fine. You don't not necessary that you need to produce the certificate. It's not mandatory. It's nobody, even in the research paper also, nobody is going to ask you to produce the calibration certificate.
Is there any
basically in research community, we trust. That is it. The trust is the this one. Even when we get the manuscript, of course, we go through all the experimental things, everything will go through it. We assume that those values, what was presented in the manuscripts are genuine and true. So with that trust only, we will evaluate the manuscript and we'll do it. And we are not going to ask any calibration certificate.
Thank you, Muthukumar. One last question. That's all. The rest of them, there are very much applauding comments on appreciations and a nice presentation. Everyone felt without a single second break, you covered so much. That's what is beauty. Sir, is there any guidelines for the for experimental setup to validate?
So that's what I given. See, at the end, I have given the design of experiment. So they need to follow it. And the only thing is, whatever the instruments they have used, there should be all the instruments need to be calibrated. And before starting the experiment, and there are some kind of a protocol, you need to go for the leak test. If you are going for the leak test, you either use argon or the nitrogen gas. Suppose we are not using any kind of a chemical reaction, if chemical reaction is involved, you need to use argon gas or helium gas, and you pressurize the whole medium, whole setup up to about 100 bar. It depends on your operating range, and allow it for maybe about 2 days and 3 days and see if there is any pressure reduction. And also you need to go for the vacuum test and maybe down to 10 raised to -3 millibar and see if there is your setup is holding vacuum or not. So for any this kind of thermal related experimental studies, you need to go for the high pressure and vacuum test, and this is very much essential. And on top of that, whatever the instruments you are using, you please ensure that all the instruments are calibrated according to your experimental condition. Then those are precisely selected. Then once you decide the proper operating range, then you can go for it. So there is, as such, of course, there is no protocol for designing the experimental setup. All these things you need to, of course, learn it from your own experience.
Yeah, thank you, Muthukumar, for the nice presentation. It's already 7:21. So 6:45, we promised already half an hour, we have taken more.
It's okay. So I will.
Yeah, really, you see, this is where a lot of people doesn't know much about instrumentation and experimental facility validation. The other things, that is where they opt for soft research instead of hard research. But you are a man with always a hard, that is hardware-based research. Excellent. So thank you, Muthukumar. Thank you for joining for this nice presentation. If you are compressed of time, you can leave. I will give a formal vote of thanks and end the session. Sir, over to a vote of thanks. Sir, dear participants, in my presentation, I'm Dr. P.S. Srinivasan. In my presentation, I will cover up. I have done an experimental work as well as CFD, computation fluid dynamics work, and modeling work. All the three combined in one experimental work, and that's what examiners have appreciated. And how to validate the experimental facility and all, I will cover in a very detailed manner. I mean, what are the difficulties you may face while really fabricating an experimental facility and validating it? So that experience I will explain in any one of both the talks I have scheduled. And many of the people have expressed that how to read a research paper, and from there how to extract the relevant information. And we have did the literature survey, from there how to coin a research problem. All those things people have requested. So these things I will cover in my talk, whatever being missed in this external resource person presentations. Thank you. You can, if you have any, sir, this attendance feedback, all those things, those who have registered, we will mail to you. And tomorrow's session, next session, we will give enough instruction. You join because of want of time. Muniraj, now go to vote of thanks and closing. Thank you. Yes, I thank everyone for joining. Thank you.
Thank you, sir. Thank you for your excellent presentation, sir. I request Dr. Gauri Shankar, please give your vote of thanks.
Thank you, sir. Yes, sir. Thank you, sir. It's my immense pleasure to propose a vote of thanks in the webinar series on research. Everyone can do quality research. First of all, I thank Dr. P. Muthukumar, Professor, Department of Mechanical Engineering, Indian Institute of Technology, Guwahati, for accepting our invitation and delivered a wonderful eye-opening lecture in instrumentation for research in thermal engineering. Thank you, sir. Next, I thank Dr. P.S.S. Srinivasan, Professor, Founder and Principal, KIOT, for providing a wonderful learning platform. Thank you, sir. I thank all the HOD and coordinators for the wonderful event arrangement and contribution. Thank you, sir. Finally, I thank the participant for their valuable presence and involvement. I hope extend their support in future also. Thank you, sir and madam.
Yeah, thank you, dear
Thank you,
participants. All the sessions are being arranged with micro level details. This session is purely technical, more related to mechanical and physics related. The CFD computation fluid dynamic talk 3, barring these two topics, all are very elementary level, and real difficulties what you may face. How to read a research paper, how to do literature survey, how to identify a research problem, and then how to identify methods of getting the thing either experimental or computational or analytical or what combination, and then this new what kind of combination, and then how to generate the experimental data and plot the data in various forms, and everything you are there, but only the final part is discussion of the results. That is where many research scholars found are finding it very difficult. I had guided 14 PhDs, and all of them had very much difficulty only in research and discussion. With our experience as a supervisor, we do that. But by going through some 2,000 plus research papers for the sake of these 14 scholars, I have found out a method, a common method with which very simply you can do research and discussion part very easily you can handle. So that experience will also we will share in our future talks. Over to Muniraj for closing.
Thank you, sir. Thank you for the brief about future webinar series. I really thank our resource students and also our principal, sir, and also all the coordinators which are coordinating this program. Now it's over to Siva in this session.
Thank you, sir. Now end the meeting.